So on average, the insertion time is going to be logarithmic, but in the worst case, this behavior could degrade to linear time. Let's have a look at that. So if our instructions are the following, insert 1, 2, 3, 4, 5, and 6. So we start at 1, then we're going to insert 2, so that's going to go to the right. Okay, now let's insert 3. Well, 3 is greater than everything, so I have to place it to the right again. Now, how about 4? Okay, 4 is also greater than everything. Oh, it looks like we're creating this line now. And now 6 is still greater than everything. So, as you can see, this type of linear behavior is really bad. And we don't want to create lines like this, because if we want to query where 6 is in the tree, or if we want to remove 5, or do anything on our binary search tree, we first need to find the node. That's going to take linear time, and this is bad. It's one of the reasons why people have invented things like balanced binary search trees, or self-balancing trees, which balance themselves as you insert nodes. We'll be getting to that later, but that's it for insertion. It's really simple. Don't overcomplicate it. Alright, now that we know how to insert elements into a binary search tree, we might also want to remove elements from a binary search tree. And this is slightly more complicated, but I'm going to make it very simple for you guys. So when we're removing elements from a binary search tree, you can think of it as a two-step process. First, we have to find the element we wish to remove within the binary search tree, if it exists at all. And in the second stage, we want to replace the node we're removing with its successor, if one exists, in order to maintain the binary search tree invariant. Now let me remind you what the binary search tree invariant is. It's that the left subtree has smaller elements than the current node, and the right subtree has larger elements than the current node. Okay. So let's dive into phase 1, the find phase. So if we're searching for an element inside our binary search tree, one of 4 things is going to happen. The first thing is we hit a null node, meaning we've went all the way down our binary search tree and have not found the value we want. So the value does not exist inside our binary search tree. Another thing that can happen is the comparator value is equal to 0. And what I mean by a comparator is it's a function that will return -1 if it's less than, 0 if it's equal to, or 1 if it's greater than the current value. So it tells us essentially which subtree we need to go down, or if we found the value that we're looking for. So if it's equal to 0, then we found the value. If it's less than 0, the value might exist, and if it does, it's going to be in the left subtree. If our comparator returns a value greater than 0, then if the value exists, it's going to be in the right subtree. Okay, let's have an example with some animation. So suppose we have 4 find queries, find 14, 25, 37, and 17. And that's our binary search tree there on the right. So if we're trying to find 14, as usual, we need to start at the root, and 14 is less than, so go left. 14 is greater than 10, so go right. 14 is less than 15, go left. 14 is greater than 12, so go right again. And now we have found the value that we are looking for. Alright, move on to 25. 25 is greater than 20. Go right. 25 is less than 31. And now we found 25. See if you can do 37 on your own. Pause the video or something. Okay, here's how it go. Go right, go left, go right. Alright, now let's have a look at 17. So 17 should be on the left. Now we should go right. Then we should go right again. And, oh, we've hit a point where we know that 17 does not exist in our tree. So that's another possibility. The value simply doesn't exist. Because we would go to the left of 19, and the left of 19 is a null node, and a null node means we haven't found the value we're looking for. So now that we found the value that we're looking for, we're at the remove phase. And in the remove phase, there are 4 cases, essentially. And the first case is that the node we want to remove is a leaf node, so it has no subtrees. Cases 2 and 3, as I like to call them, is there's only one subtree. Meaning there's a right subtree but no left subtree, or there's a left subtree and no right subtree. Or finally, case 4 is that we have both a left and a right subtree. So I'm going to show you guys how to handle each of these cases, and it's really not that hard. So case 1, we have a leaf node. So if you have a leaf node and you want to remove it, then you can do so without a side effect, which is really nice. So suppose we have the binary search tree on the right, and we want to remove 8. So we do phase 1, we find out where 8 is. Oh, and 8 is a case 1 because it's a leaf node, so we know we can remove it without side effect, so we remove it. Perfect, that wasn't hard. Now let's look at cases 2 and 3, meaning that either the left or the right child is a subtree. In this case, the successor of the node we're trying to remove is going to be the root node of that left or right subtree. Let's look at an example. Suppose we want to remove 9. So first let's find 9. Okay, we found 9. Now we encounter a case 2 with a left subtree, because 9 doesn't have a right subtree. So the successor is going to be the root node of that left subtree, so 7. So now I can remove 9, and 7 becomes the successor of 9. Perfect. Now let's do another example where we want to remove 4. So first let's find 4. So we find 4, and this is our other case where we only have a left subtree but no right subtree. So what do? The successor of 4 is going to be the root node of that left subtree, so 3. So we can remove 4, and now 3 becomes the successor. Alright, that wasn't so bad, was it? Alright, so now for case 4, now we want to remove a node which has both a left subtree and a right subtree. Now the question is, in which subtree will the successor of the node we're trying to remove be? And the answer is both. The successor can either be the largest value in the left subtree or the smallest value in the right subtree. And here's perhaps some justification for why there can be 2 successors. So the largest value that we can find in that left subtree would satisfy the binary search tree invariant if it becomes a successor, because it would be larger than everything in the left subtree, and this is immediate from being the largest in the left subtree, and also it would be smaller than everything in the right subtree because we had found it in the left subtree. Similarly, if we find the smallest value in the right subtree, it would also satisfy the binary search tree invariant for the following reason. It would be smaller than everything in the right subtree, and this is immediate from being the smallest in the right subtree, and also larger than everything in the left subtree because it was found in the right subtree. And we know things in the right subtree are, well, greater than everything in the left subtree. So we come to this conclusion that, well, there must be 2 possible successors. So we can choose either or. Fantastic. So if we have this tree, and we want to remove 7, well, 7 is a case 4 because it has both a left subtree and a right subtree. So 7, so find 7, we've already found it. And now we get to either pick the successor in our left subtree or our right subtree. I'm going to find the smallest value in the right subtree. What we do is we go into the right subtree and then we dig as far left as possible. Go left and go left again, and now we don't have a left child, so we can stop, and this node is going to be the successor. It is the smallest node in the right subtree. And you can see that quite clearly. 11 is smaller than everything in that right subtree. So now what we want to do is we want to copy the value from the node we found in that right subtree, 11, into the node we wanted to originally remove, which is 7. So now I replace 7 with 11. Now we have a problem, which is we have 11 twice in our subtree, and we want to now remove that element 11, which is highlighted, because it is the successor. It shouldn't no longer be inside the tree. And luckily for us, the successor node we want to remove is always going to be either a case 1, 2, or 3 removal. So in this case, it would be the case where there's a right subtree but no left subtree. And you would just do this recursively, so it would just call itself and it would hit one of those 3 cases. Okay, so it's a right subtree, so what we want to do is swap it with the root node of that right subtree and then remove it. So remove 11. 14 becomes a successor, and now just going to rebalance the tree like that. Alright, now let's have a look at another case. In this example, let's remove 14. So first, let's find 14 if it exists within our tree. Go right. Alright, we found 14. Now we either want to find the smallest value in the right subtree, like we did last time, or the largest value in the left subtree. So now let's do the latter this time and find the largest value in the left subtree. To do this, what we would do is we would go into the left subtree and dig as far right as possible this time. Go into the left subtree and dig as far right. 9, 13. Now 13 is the largest value in the left subtree. And now what we want to do, as per before, is we want to copy the value of the successor, 13, into the node we want to remove, which is 14. So now 14 becomes 13, and now we want to remove the remaining 13. So now just remove it and replace it with the successor. Perfect. Okay, I just want to go over some more examples, so just these 2 short examples, because removing is not quite so obvious. Alright, let's start with the one on the left. So let's see if we can remove 18 from this strange looking binary search tree. So start at the root, find 18, so dig all the way down. Okay, we found 18, and now we want to, it's one of those case 2 or 3s. It's the one where there's a left subtree, so the successor is just going to be the root node of that left subtree, or 17. So remove 18 and replace it with 17, so 17 is the new successor. Perfect. Now let's look at the other case where we want to remove -2. So now first find -2, so go to the left. Okay, we found it. Now there's 2 subtrees. Pick one of the 2 to find its successor. I'm going to go to the right. Alright, copy its value in, and now remove -1, and that's it. Okay, and that is removals in a nutshell. Alright, I want to finish off binary trees and binary search trees with some tree traversals, in particular pre-order, in-order, post-order, and level order. You see these tree traversals come up now and again, so they're good to know. I want to focus on pre-order, in-order, and post-order to begin with because they're very similar. They're also naturally defined recursively, and you can sort of get a feel for why they have their certain names that they do. So pre-order prints before the two recursive calls. In order will print between recursive calls, and post order will print after the recursive calls. So if you look at the three functions on the left, the only thing that's different between them is where the print statement is. So let's go into some detail on how pre-order works. So on the right, I'm going to maintain a call stack of what gets called. So when we're recursing back up, we know what called us to know what node to go to. And what you need to know about pre-order is that we print the value of the current node, and then we traverse the left subtree followed by the right subtree. So for our order, what we're going to do is we're going to start A, print A, then we go left, go to B, then we go down to D, go down to H, and now we recurse back up. So we push node H off the call stack and go to D, and then we go to I, and then we explore I. Now we're at the bottom, so we recurse back up, so we push I off the call stack. We've already processed D, and we go back to B. We've also already processed B, but now we have to do B's right subtree. So we go and explore E. Now we've explored E, so push the frame off the stack, explored B, push that off the stack, and now A. Now we need to explore the right subtree of A. So we would print C, then F, then J, and then we're at the bottom, so recurse, and then now K, and now we're at the bottom, so recurse, so push node K off the stack, push node F off the stack, and now explore node C's right subtree. So G, now L, and now we're done. We curse all the way back up, and we would exit our function. And at the bottom, you can see what the pre-order traversal is. Okay, now let's cover in-order traversal. So how in-order traversal works is we traverse the left subtree, then we print the value, and then we traverse the right subtree. And for this example, I'm going to be using a binary search tree and not just a generic binary tree. And you'll see something interesting happens. We push node 11 on the stack because it's our root. Then we go left. Then we go left again. Then we go left again. And notice as I was going left, I would push those on to the stack, but I'm not printing the value yet because when I call in order, the very first instruction in the in order is to go left. I only print once I've traversed the entire left subtree. If I'm a leaf node, like I am now, one is a leaf node, then I've already explored the left subtree, if you will. So I can print the current value, then I recurse, and then I print 3 because I've explored 3's left subtree. Now we can go right now, and I've explored both subtrees, so I can print 5, and I recurse. Now I can print 6 because I've explored 6's left subtree, and I can go to 8, then recurse, and then print 11, Now we need to finish 11's right subtree. So go right, go left, now explore 12, recurse, and we're going to print 13, then go down to 14, print 14 also because 14 has no subtrees. Go up, so push 14 out the stack, push 13 out the stack, print 15 because we will explode 15's left subtree, go right, and now the last thing we need to do is finish our function by just pushing everything off the stack. So go back up. And now, did you notice something interesting happened when we did our in-order traversal? Well, what happened was we printed the values of the nodes in increasing order, which is why it's called an in-order traversal if you do it on a binary search tree. It prints the values in increasing order, which is really neat. That's quite a nice property of the in-order traversal. Now let's look at the post-order traversal. And the post-order traversal says, okay, traverse the left subtree, then traverse the right subtree, and after you're done doing both of those, only then print the value of the node. So this means if you look at our tree right now, the last value we're going to print should be 11, because we need to process 11's entire left subtree and 11's entire right subtree. So let's start at 11 and explore its left subtree. So go all the way down, then print 1 because we've explored both its left and right subtree. Now don't print 3 because we haven't explored its right subtree yet. Print 5 because we've explored both its subtrees, which don't exist. Now we can print 3 because we've explored both of its subtrees. And then similarly go down to 8, print 8, recurse, and print 6. Don't print 11 because we still need to do its right subtree. Go to 15, 13, 12, print 12. Go up to 13, print 14, go back up to 13, and now we can print it. Don't print 15 yet because we haven't explored all of its right subtree. Then go to 17, 19, and then pop everything off the stack and print on the way back up. And you can see that 11 is indeed the last node we have visited. And that's pre-order, in-order, and post-order in a nutshell. Now I want to look at level order traversal, which is special. It's quite a bit different from the other two. A level order traversal is we want to print the nodes one layer at a time. So start with 11, then we want to print 6 and 15, then 3, 8, 13, 17, and 1, 5, 12, 14, and 19. And you're like, oh, how am I going to do that? And the way we're going to obtain this ordering is by doing something called a breadth first search. From the root node all the way down to the leaf node. So if you know what a breadth first search is from graph theory, and this is the same thing. A tree is a type of graph. It's no different. So what we're going to do our breadth first search is we're going to maintain a queue of the nodes we have left to explore. And how this is going to work is our queue is originally going to contain only the root node. And we're going to keep processing by pulling out the first value in our queue until our queue is over. A bit more detail on that. So here you can see the queue on the right. I've inserted node 11, and so I would pull out node 11 and I would add 11's left child and 11's right child to the queue. So they would go at the end of the queue, and I've also removed 11. So the next node process would be 6, followed by 15. And then I would keep adding children to the queue so that I reach them eventually. So let's have a look. So I've pulled 11 from the queue and now added 6 and 15 to the queue. Now the next thing on the top of the queue is 6, so I'd remove 6 and add 6's children 3 and 8 to the queue. Then 15 is next up. Now I'd add 15's children, which are 13 and 17 to the queue. And next up in the queue is 3, so I would add 3's children to the queue, and then move on, explore 8. 8 has no children, so I can't add them. Next, 13. And you can see that as I'm exploring nodes, I just add the children, but keep pulling the most recent thing in the queue. And this gives us the level order traversal that we want. And this is how you do a breadth first search in general. So not too complicated, except we had to use that special trick of using a queue instead of using a stack. So we don't do level order traversals recursively. We need to do them iteratively with a queue. Okay, finally time to look at some source code for a binary search tree. So the source code that I'm about to show you can be found at the following link. The link should also be in the description at the bottom of this video. Please like the repository so that other people can also find it more easily. And now let's dive in. Alright, here we are inside the source code for the binary search tree. This source code is written in Java. Okay, so first thing you will notice is I have a class representing a binary search tree, and it takes as a type anything that is comparable. We need things that are comparable so we know how to insert them accordingly within the binary search tree. So to start us off, I have a few instance variables. Actually, only 2 in fact. One to keep track of the number of nodes in the binary search tree, and another one which is the root of this binary search tree, because this binary search tree is a rooted tree. Next, I have a private node class, which contains a left node and a right node, as well as some data of type T. And that type T comes from here. So it's some comparable type T. Okay, next I have a method to check if our binary search tree is empty. It simply checks if the size is 0, and size simply returns the node count, which gets either incremented or decremented as we add or remove elements. Okay, here's the public method to add elements to this binary search tree. I also have a private method down here, as you will notice. And I use the private methods to do the recursive business, and the public method to just check if the element is already contained within the binary search tree. This insertion method will return true if we successfully insert a new element into the binary search tree, and it will return false if there's already something inside the binary search tree. So elements have to be unique inside this binary search tree. Okay, so supposing this branch doesn't get executed, meaning the element does not already exist in the tree, then we're looking at this branch. And I'm saying, okay, add this new element to the binary search tree recursively, and also up the node count by 1, and return true because, well, this element doesn't yet exist. So let's look at the recursive method now. So our base case is that we found the null leaf we want to insert our element at. So we would create a new node object with 2 null children, but with the value of the element we want to insert. Otherwise, we're in this branch, and we choose which subtree we want to place our element inside. So either it's going to be the left subtree, the first branch, or the right subtree, the second branch. Okay, now let's look at removing. So here's the public method for removing, and I'm only going to remove the method if it exists within the tree. So I check if it's within the tree before, otherwise I'm just going to return false, meaning we have not removed anything from this binary search tree. And if it is contained, then I'm also going to decrement the node count. Now let's look at this recursive method to remove the node. So this recursive method simply has a normal base case. If it's null, return null. And in the first step to removing a node, we first have to find it. And we know it exists because of this check. We know that our element is within the tree, so we can remove it. And that is these two cases. So this is like the find phase I was talking about in the later video. So I get a comparator value and I check if it's less than, so we're going in the left subtree, or we're going inside the right subtree. It's going to be one of these two cases. Otherwise, we found the node we want to remove. So this finds the node, and here's where we do the actual removal. So I talked about 4 cases in my slides, but in fact you can think of it more or less as 3 cases, even 2 cases, because 2 of the cases are very similar. So the singleton case, where there's only one node, it's really that can also be thought of as a left subtree or a right subtree case. This case is the case where the left subtree is null, but the right subtree is not. And this case, the right subtree is null, but the left subtree isn't. And this case down here, which I'll get to later, we have both subtrees. So let's go to the very top. So if we only have a right subtree, then I'm going to say that the successor node is just going to be the root node of that right subtree. So node.right. And then I return that. And I also destroy the data within this node and the node itself. Similarly, for the other case where I only have a left subtree, what I'm going to do is I'm going to reach into that left subtree and grab the root node. And I'm going to return that node. And I'm also going to destroy this node because we know we don't want it anymore. So those 2 cases are fairly easy. Now let's look at the case where we have a left subtree and a right subtree. So as I mentioned in my slides, we can either find the largest node in the left subtree or the smallest node in the right subtree. And here I find the smallest node in the right subtree. So I go down to the right subtree and I dig left. And this is the node, or the successor node, if you will. So we copy the data in it, and then we recurse and call ourselves to remove the successor node. If you wanted to find the largest value in the left subtree, then you could just uncomment this code, and it would do just that. So that's removing in a nutshell, and I also had these 2 helper methods to do a dig left and a dig right. Moving on, I also have this method that checks contains of an element. So given an element, it'll return true or false depending on if that element is within this binary subtree. And this is very simple. This is equivalent to the find phase. If we reach a null node, we definitely know that that element doesn't exist. Otherwise, get our comparator value, which is either going to be less than if we need to go to the left subtree, meaning this case, or greater than 0 if we need to go in the right subtree, or if we found the element, then that's the 0 case, and we're in this case. So pretty simple. Just as a bonus, I also threw in a height function. So this will calculate the height of the tree. It'll do so in linear time. Height we'll call the private recursive height method. And all this does is, it's fairly simple. So if we reach a leaf node, we're going to return 0. Otherwise, we're going to return the maximum height of the left subtree or the right subtree, because one of our subtrees might be greater than the other, and that's going to be the one that we want the height from. But every time we recurse, we add +1. So this corresponds to a depth. So the biggest depth is going to be whatever the height of the tree is, if you want to think of it that way. And now for our traversals, I have created this method called traverse. And what it does is it takes a tree traversal order, which is an enum type. I'm going to show you in a minute. And that's an order, and then I pick whichever order you give me, and I return an iterator for that particular order I want to traverse. So if you tell me I want to traverse this binary search tree in a pre-order fashion, then I'm going to return you this iterator, which is this method. If you want to traverse the tree in order, I'm going to return you this in order traversal iterator. Let's have a look at what this tree traversal order is. Let me open that up right here. So that is simply an enum type. You can see right here. So it's either one of these 4 things. It's pre-order, in order, post-order. So nothing too crazy. And I decided to do these traversals iteratively so that you don't have to do them recursively, which would be slightly slower and perhaps less convenient. This is more flexible, although I don't really want to dive into the code because it is fairly nasty. If I just open up, say, the in-order traversal, then it does look pretty gross. I have to maintain a stack manually, and I have to check for concurrent modification errors, etc., etc., etc. These are actually great interview questions, like how do I do an in-order traversal iteratively, or how do I do a post-order traversal iteratively, and so on and so on. So those are definitely great to practice. If you want to actually see what's hidden inside these methods, just go on the GitHub repository and have a look. But I showed you guys how to do tree traversals in the last slides, so you should be good to do that. Most of the time you do it recursively anyways. I just want to be a bit more fancy and go all out iteratively. So this is about it for the binary search tree. Today we're going to be talking about hash tables, one of the most remarkable data structures of all times. If I had a subtitle, it would be one data structure to rule them all. So let's get started. There's going to be a lot of things to cover in the hash table series. We're going to start off with what is a hash table and what the heck is a hash function and why do we need one. Then we're going to talk about some popular collision resolution methods, In particular, separate chaining, open addressing, those are the two most popular ones, although there's a ton more. Then we're going to separate chaining with linked list, just because it's a really popular implementation. And there's a ton of stuff in open addressing that needs to get covered. So we're going to be talking about linear probing and quadratic probing, how that's done. I'm going to be giving lots and lots of examples for those, just because it's not super obvious how they work. And to finish off, we're going to be going over double hashing and finally removing elements from the open addressing scheme, because that's not so obvious either. Alright, so to begin with, what is a hash table? So the hash table is a data structure that lets us construct a mapping from some keys to some values via a technique called hashing, which we'll talk about shortly. So the key could be any value, as long as it's unique, which maps to a value. So for instance, keys could be names, which are people names, and the value could be someone's favorite color. So William's favorite color is green, Micah's is purple, Catherine's is yellow, and so on. And we call these key value pairs. So each key is associated with a value. So all of the keys have to be unique, the values don't have to be unique. For example, Micah's favorite color is purple, but also Leah's favorite color is purple. We often use hash tables to track item frequencies. For example, below is a frequency table of the number of times a certain word appeared in Shakespeare's Hamlet, which I parsed and obtained this table. So you can see Hamlet appeared 114 times, the word Lord 223, but the word cabbage did not appear. So hash tables are often used to track frequencies, which is really handy. But you can really construct a mapping between any key value pairs, given that the keys are hashable. This is something we're going to talk about shortly. So to be able to understand how we construct the mapping within the hash table, we need to understand what a hash function is. So simply put, a hash function, which I will denote from now on as h of x for some key x, is a function that maps x to a whole number in some fixed range. So that's pretty simple. Let's have a look at an arbitrary hash function. So if our hash function is h of x equals some polynomial x squared minus 6x plus 9 modulo 10, well, all the integer keys get mapped to the range 0 to 9 inclusive. No matter what integer number I plug into h of x. So below, I'm plugging in certain values or keys, if you will, into the hash function and getting an output. So notice that the output is not unique in that there could be two values that I plug into the hash function which yield the same value. For instance, h of 4 and h of 2 map to the same thing, and that's completely fine. So we can also define arbitrary hash functions, not just on integers, but on arbitrary objects, which makes this really powerful. For instance, suppose we have a string s, and we're going to say h of s be the hash function that I've defined below. So this hash function, all it does is it sums the ASCII values of the characters within the string, and then at the end says modulo 50. So that will, for any given string, just output a number, and that's a hash function. So for example, some simple inputs. So h of bb gets 66 plus 66, and then we mod that by 50, so we get 32. The empty string gets 0 because we don't even execute the loop, and so on. So we've effectively converted a string to a number. Great. Alright, here's a mini challenge for you. Suppose we have a database of people below, and each person has 3 fields. They have an age, a name, and a sex. I want you to define a hash function, h of a person, where you're going to be given a person object as an argument. And I want you to create a hash function that's going to map a person to the set of values 0 through 5 inclusive. You can pause the video, just create any hash function that does this given the 3 fields. Alright, so here's my attempt at creating such a hash function. Turns out there is an infinite amount of possible hash functions we could have defined for the hash of the person. And here's a simple one. So I'm going to say, okay, first let's start with the age. So whatever there is, that's the starting value for the hash. Then I'm going to add on the length of the person's name, again an arbitrary choice. And I'm going to increment by 1 if they're males, and then mod by 6. So as you can see, hash functions are a bit arbitrarily defined at this point. We're going to get into some more sophisticated hash functions later. So this particular hash function yields those values. Alright, something very important, very important we need to talk about are properties of hash functions. So if we have a hash function and 2 objects, say x and y, and their hash values are equal, then those 2 objects might be equal. We don't know for sure. We have to explicitly check x against y, because the hash function tells us that there was a collision right there. But if the hash functions are not equal, then x and y are certainly not equal. Here's a good question. How can we use this to our advantage to speed up object comparisons? The answer is that instead of comparing x and y directly, if we've already computed their hash values, then first let's compare the hash values of x and y instead of comparing x and y explicitly. And in this next example, you'll see why that's important. Consider the problem of trying to determine if 2 very large files have the same contents. This is something you want to do in an operating system context all the time. So if we've computed the hash values for file 1 and file 2, first we should compare the hash values together to see if they match or don't match, because this requires constant time work, which is super fast. So if possible, we don't want to open the files at all. This would be comparing x and y directly, or file 1 against file 2. But we will have to compare them byte per byte if their hash values are equal. So actually, hash functions for files are much more sophisticated than those that we use for hash tables. Instead, we use very sophisticated hashing algorithms called cryptographic hash functions and checksums. Alright, another property of hash functions is that they must absolutely be deterministic. This means that if h of x produces y, then h of x must always produce y and never another value. This is super critical because this will screw up our hash table completely if this happens. We do not want this. So an example of a non-deterministic hash function is something that introduces, say, a global variable or some kind of randomness. You don't want that. So in this particular hash function, the first time I run it, the hash value for 5 is 6, but then if I call it again, we've incremented the counter and now the hash value is 7. Uh-oh, not good. Something else about hash functions is we try very hard to make them uniform. To minimize the number of hash collisions, we'll get into why hash collisions are bad shortly, but a hash collision is when 2 objects, x and y, hash to the same value. That is, h of x equals h of y. And the reason we want it to be uniform is so that all the values of our hash function are hit. so that we can fill the table uniformly. So for example, the table we generated earlier, William and Kate, they have a hash collision. Uh-oh. Okay, so now we're able to answer a central question about the types of keys that we're allowed to put in our hash table. So what makes a key of type T hashable? Here's the answer. Since we're going to implement our hash table using these hash functions, we need those hash functions to be deterministic. And to enforce that behavior, you'll see a lot of programming languages enforce that the keys you use be immutable, meaning you can't change them. They're fixed, they're constants. So they're things like immutable strings, integers, but not things like sets or lists or things you can add or remove things from. They're immutable. And if we have that condition, and we have a hash function that is defined for all keys of type T, then we say that that type is hashable. Okay. All right, so now let's get into the interesting details. How does the hash table work? Well, ideally, we want our hash function to have really quick insertion, lookup, and removal times. And remarkably, we can achieve all of that using the hash function as a way to index into a hash table. And a hash table is just a fancy word for an array. Think of it like that. Every time I say hash table, think array. So again, we use the hash function as a way to index into the hash table. So the hash function gives us an index to go look up inside the table. And yes, we can do this in constant time, given that we have a uniform hash function. Super essential. Okay, think of the hash table on the right as an indexable block of memory. So, as I said, an array. And we can access these entries with the hash function, h of x. So suppose we're going to be inserting integer string key value pairs into the table that are going to represent rankings of users to their usernames, say in an online programming competition. And this is the arbitrary hash function that we chose, x squared plus 3 mod 10. All right, let's get started. So if I want to insert the key value pair 3 byte eater, so in the contest, the user whose username is byte eater got a rank of 3, and we want to insert that into the hash table. Then what we do is we hash the key, which is 3, and we get h of 3 being 3 squared plus 3 mod 10, or 2. So in our hash table or array, at index 2, we're going to put the key be 3 and the value to be byte eater. All right, now this next user, WilliamFiset, which is usually what I call myself in online programming competitions, he is rank 1, and if we hash 1, then we get 4. So at index 4, then we're going to put the key and the value for William, or will.fiset. Next, if we want to insert Lauren, 425, who's got rank 32, again we hash 32, and we put her in the table where she goes. Then we can do the same thing for Ternary Wizard, who has rank 5, and insert Orange Knight, again by hashing the key, finding out where it goes. So as we keep doing this, we keep filling the table, but eventually we're bound to have a collision. Now, in the event that we want to do a lookup for a user that has a rank R, all we need to do is compute the hash value for R and then look inside our hash table to see where this user is. So say I want to find the user with rank 10, and I hash 10, figure out its index is 3, and then I get the value, which is the Orange Knight, has rank 10. Great. However, how do we handle hash collisions? For example, users who have ranks 2 and 8 have the same value. This is problematic because we don't have another place to put them inside our table. They would index into the same position, yeah? And the answer is we use one of many hash collision resolution techniques to handle this. There are many, but the two most popular ones are separate chaining and open addressing. The idea behind separate chaining is that we deal with hash collisions by maintaining a data structure, usually a linked list, to hold all the different key value pairs which hash to some particular value. Open addressing is slightly different. It deals with hash collisions by probing and finding another place within the hash table offset from the place where we originally hashed to. So in open addressing, everything is kept inside one big array. In separate chaining, you have multiple auxiliary data structures. So the time complexity of the hash table is actually pretty remarkable. In fact, it's amazing. So on average, we can achieve constant time for insertion, removal, and search, but if you have a terrible hash function that's not uniform, then you can get linear time, which is really, really bad. Okay, let's talk about something super cool, and that is hash tables and separate chaining. Alright, let's dive right in. What is separate chaining? So separate chaining is just one of many hash collision resolution techniques. And how it works is when there's a hash collision, meaning two keys hash to the same value, we need to have some sort of way of handling that within our hash table so that's still functional. Well, what separate chaining does is it maintains an auxiliary data structure to essentially hold all the collisions. And so we can go back and look up inside that bucket or that data structure of values for the item we're looking for. And usually we use a linked list for this, but it's not limited to only linked lists. We can use arrays, binary trees, self-balancing trees, or even a hybrid approach. Okay, so suppose we have the following hash table, which is just a fancy name for an array of key value pairs of age and names. And we associate an arbitrary hash value that has been computed with some hash function. So those are our hash values. They don't really matter for now. We're just going to see how we can use separate chaining to handle the collisions. Okay, so on the left is our hash table, so our array. And I'm going to be inserting all of these key value pairs into this hash table via separate chaining, and you'll see how easy it is. Okay, so our first person is Will. His age is 21, and he hashed to 3. So we're going to put him in that slot 3. Leah, age 18, hashed to 4. Since she hashed to 4, we're going to put her at index 4. So the hash is a way to index into the array. Okay, Rick, age 61, hashed 2. We're going to put him there. And Ray, age 25, hash 1. Okay, we're starting to get a little bit full in our hash table here, so we might get some collisions pretty soon. Okay, Lara, age 34, hash to 4, but we say, oh shoot, Leah is already there. What do we do? Well, in separate chaining, we just chain along. So essentially each position in the array is actually a linked list data structure. So we're going to scan through the linked list and see if Lara exists, and if Lara does not exist, then we're going to add Lara at the very end of the chain. Okay, so Ryan also hashed to 1, but then we look and Ryan is not equal to Ray, so we need to add a new entry at position 1. Now Lara, age 34, 4, hash to 4, so nope. And oh, Lara already existed in our hash table, so we're good. And she still has the same age, so we don't need to update it. So Finn, age 21, hash to 3, so he's got a hash collision with Will, who had also hashed to 3. So what we're going to do is we're going to append Finn to the end of the linked list chain. So note that even though that Will and Finn both hashed to the same value, that is index 3, and they have the same age, we tell them apart because we store both the key and the value as an entry in our linked list block. So that's how we're able to tell them apart. Okay, now I want to insert Mark, whose age is 10 and who hashed to 4. So scan through the linked list at index 4 for Mark, and he's not found, so we have to append Mark at the very end. Alright, now let's have a look at how we can do lookups in this structure. So it's basically the same thing. So what we're going to do is, given a name, we want to find, well, what the person's age is. So suppose we have Ryan, and Ryan, when we hash him, we get 1. So we suspect that Ryan should be in bucket 1. When I say a bucket, I just mean whatever data structure we're using at index 1. In our case, a linked list. So I have to scan this linked list for Ryan. So we start array, no. So here we're comparing the key. So we're comparing the key Ryan to the key array. And there's not a match, so keep going. Compare Ryan to Ryan, there's a match. Okay, we found Ryan, and then inside that entry we say, oh, his age is 56. So return 56. Okay, let's do another one. Find the age of Mark, hash Mark. And since our hash functions are deterministic, we know that if there's a Mark, then it's going to be found in position 4. Okay, so we look into bucket 4, scan through. Oh, the last one is a Mark, so we return age 10. So it might happen that the value or the key you're looking for doesn't exist, and so it doesn't exist. You return null. Okay, so here's a good question. How do we maintain a constant time insertion and lookup time complexity if the hash table gets really full and I have some long linked list chains? Good question. And the answer is that once there's a lot of elements within your hash table, you'll actually want to create a new hash table with a larger capacity and rehash all your items and reinsert them into this new larger table, because tables are fixed size. Okay, and another good question, how do I remove key value pairs from my hash table with separate chaining? Well, the answer is basically the same procedure. You hash your key, and instead of doing a lookup, well, you would remove the particular entry in the linked list. That's it. Another question, can I use another data structure to model the bucket behavior of separate chaining? And yes, of course. And common data structures that are used inside of a linked list include arrays, binary trees, self-balancing trees. Java uses a hybrid approach in their hash map. So once they get to a certain chain length, they switch to a binary tree, or maybe a self-balanced binary tree, I'm not too sure. However, these alternative methods are a bit more memory intensive and complex to implement, which is why they may be less popular, but they might be a lot faster too. I haven't actually implemented them myself. Alright, it's time to have a look at some separate chaining source code for the hash table. So here I am on my GitHub repository, WilliamFiset/data-structures, and you can find the source code here under the hash table folder. Now I have multiple implementations of the hash table. Today we're going to be looking at the hash table with separate chaining, and in the later videos probably one of these 3. I haven't figured out which one yet. So let's dive into the code. I have it here on my computer, so let's get going. Alright, so first things first, I have 2 classes. One of them called entry, the other one just separate chaining hash table. So let's have a look at the entry class first. And these entries represent individual items or key value pairs you would want to be inserting into the hash table. So in Java we have generics. So a generic key which has to be hashable and some value. So when I create an entry, I give it the key value pairs, and I also compute the hash code. So there's a built-in method in Java to compute the hash code for a particular object, and you can override it to specify the hash code for your particular object, which is really convenient. So compute the hash code and cache it. You absolutely want to cache it so you don't have to recompute this thing multiple times. It should be cheap to compute, but for something like a string, the hash code can take linear time to compute, which is not good. So here I have an equals method, which doesn't override the object equals method because I don't want to have to do any casting. First, it checks if the hashes are not equal. If the hashes are not equal, we know from the first video that they are absolutely not equal, so we can return false. Otherwise, I compare the keys to each other. And that's about it for the entry class. Very, very simple, very basic. Now let's get into the meat of the thing, so the hash table itself. Okay, so my default hash table capacity is going to be 3, so it holds three items. And the load factor by default, if the user doesn't specify one, is going to be 0.75. So that's the maximum capacity I'm willing to tolerate. Then I have a few important instance variables we need to go over. So the maximum load factor. So once the load factor goes above this value, then I resize the table. So this is the capacity, so the actual maximum number of items that could, or how big the table size is rather. So the threshold, so this is computed to be the capacity times the max load factor. So it tells us, hey, you're above the threshold to resize, it's time to resize. Size is how many items are currently in the table. And this is the table itself. So it's an array of linked lists which themselves have entries. Pretty simple. So there's a few constructors, so you can construct a hash table just using the default settings with an initial capacity or with a capacity and a max load factor. So this is a designated constructor. Let's have a look. So just save what the max load factor is, compute the default capacity, and make sure you take the max of, say, the default capacity and capacity, just so that, I don't know, you don't want the capacity to be too low. There might be weird things happening if the capacity is set to 1 or something like that. Then calculate the threshold, and then finally initialize the table. Pretty simple. Okay, let's have a look at all these methods right here. So size returns number of elements inside the hash table. Empty is the hash table empty. Okay, so this is the first really interesting method. It's called normalize index, and it's used when you want to convert a hash value into an index. And it says in the comments here, essentially this strips the negative sign and places the hash value in the domain 0 to capacity. Because hash values are integers, they could be anywhere in the domain of an integer, which is about minus 32 to the 31, to positive to the 31, around that. So what this does is a mask. It strips off the negative sign from the hash value and then mod it by the capacity. So bring it into this domain so we can actually use it as a lookup index. Next up is clear, so we just want to clear everything out of the table. That's straightforward. Contains key and hash key are the same thing. So what we're going to do is compute, given a key, so we want to find out, does this key exist within the hash table? Alright, so what we're going to do is compute the key's hash, normalize it, and then that'll give us the bucket index. So which bucket should this key appear should it be in the hash table. Now I'm just going to seek to see if I'm going to seek to find the entry. If the entry is not equal to null, then it exists. If it's equal to null, it doesn't exist. Simple. Okay, put, add, and insert are all common names for just putting something into the hash table or updating a value inside the hash table too. So we don't want to allow null keys. That's something we absolutely don't want. So just throw an exception there. Otherwise, we're going to create a new entry, find the bucket it belongs to, and then insert it using this method we'll get to. Okay, get. So given a key, I want to find the value associated with that key. Again, don't allow null keys. And this is going to be pretty routine all the time. We're always going to want to find which bucket this particular key belongs to. So get the bucket index. Okay, find the entry. Assuming it's not null, then this is the entry we want and return its value. If it is null, well, the key doesn't exist, so return null. Okay, suppose we want to remove a key now from the hash table. So key is not null, find the bucket index, and we're going to call it this private remove entry method, which is just down here. So given the bucket index, so which bucket does this key belong to? What we're going to do is we're going to seek for the entry inside the linked list structure. And if the entry is not null, then we're going to extract the actual linked list and remove it. So this is a built-in data type in Java. So just remove it from that linked list data structure, decrement the size, and return the entry value. That's all we have to do. Otherwise, it's, well, not there, so return null. So insert bucket, insert entry. So given a particular bucket, we want to place this entry inside of it. Okay. So first, since we know the bucket index, we can go in our table and automatically get the linked list structure, which I call bucket. So bucket is null. Well, we have to create a new linked list. So we're essentially lazily allocating these linked list data structures, which is good because we don't want to use more memory than we need to. So next up, I find the entry that already exists. So this is in case we want to do an update, for instance. So if the existent entry is null, this means that we need to add a new entry to the end of the linked list. So add it to the end of the linked list, increment the size, and check if we're above the threshold, and if so, resize the table. And yeah, use null to indicate that there was no previous entry. Otherwise, we need to update that entry. So then just update the value in the existing entry and return the value. Alright. So seek entry, this is a method we've been using pretty much everywhere. And it finds and returns the particular entry at a given bucket index if it exists, otherwise just return null. You probably know what's going on by now. So extract the linked list at the particular bucket index. Otherwise, return null if it doesn't exist yet. Otherwise, seek through each of the entries in the linked list and compare the keys to the key we're after. And if there's a match, return that entry. Otherwise, return null. Okay, here's the last really complicated method called the resize table. So this resizes the initial table, doubling this capacity of the table. So first we double the capacity. We recompute the new threshold because now we have a higher threshold because we've increased the capacity. Now create a new table with this new capacity. So this new table is bigger than the current table. Then go through the current table, look for linked list data structures which are not null. If you find one, we'll loop through all its entries, calculate the bucket index, find the bucket and essentially insert it into this new table. And after that, completely remove the old data that was in the old table. And at the end, set the table to be equal to the new table. Okay. And then these last two methods are just return all the keys and all the values within the hash table. Fairly simple. And then these last two methods are iterators and toString, which we don't need to go over. So that's essentially separate chaining in a nutshell. Fairly simple to implement with a linked list, much more difficult to implement with, say, a balanced binary tree or something like that. I'm pretty excited. We're going to be talking about the open addressing collision resolution technique for hash tables. So let's get going. First, let's just do a quick recap on hash tables so that everyone's on the same page. So the goal of the hash table is to construct a mapping from a set of keys to a set of values. And the keys need to be hashable. Now, what we do is we define a hash function on the keys to convert them into numbers. Then we use the number obtained through the hash function as a way to index into the array or the hash table. However, this isn't a foolproof method because from time to time we're going to have hash collisions. That is, two keys that hash to the same value. So we need a way to resolve this, and open addressing is a solution for that. Alright, so when we're going to be using the open addressing collision resolution technique, the one thing you need to keep in mind is the actual key value pairs themselves are going to be stored in the table itself. So as opposed to, say, an auxiliary data structure like in the separate chaining method we saw in the last video. So this means that we care a great deal about the size of the hash tables and how many elements are currently in the hash table. Because once there are too many elements inside the hash table, well, it's going to be really hard to find an open slot or a position to place our element. So just an important piece of terminology, we say that the load factor is the ratio between the number of items in the table and the size of the table. So this means we need to keep tabs on the load factor. Here's a neat chart from Wikipedia. So on the chart, what you can see are two different methods. One of them is chaining, that is separate chaining, and linear probing, an open addressing technique. And what you can see from the linear probing one is that once it gets to a certain threshold, it gets exponentially bad. So you don't want it to go anywhere near that, say, 0.8 mark. In fact, we're going to be keeping it a lot lower than that usually. And what this says is we always need to keep the load factor, which we denote by the Greek letter alpha, below a certain threshold. And we need to grow the size of our table once that threshold is met. Alright, so when we want to insert a key value pair into our hash table, here's what we do. We take the key, we use our hash function, define on our key, and we hash the value, and this gives us an original position inside the hash table for where the key should go. But suppose there's a hash collision, and there's already a key in that slot. Well, we can't have two keys in the same slot. That's not how arrays work. So what we do is we use a probing sequence, which I will define as P of X from now on, to tell us where to go next. So we hashed to the value h of k, the original position, and now we're going to probe along using this probing function in such a way that we're going to eventually find an open slot along the way. So as it turns out, there are actually an infinite amount of probing sequences to choose from. So here are a few of them. We have linear probing, which probes via a linear function. So given an input parameter x, so when we're probing, we start usually x at 0 or 1, and as we're unable to find free slots, then we just increment x by 1, and it works the same for all of these probing functions. For linear probing, we use a linear function. For quadratic probing, we use a quadratic function. And then there's double hashing, which is super neat actually. What we do is we define a secondary hash function on our key, find its value, and then use that inside the probing function. And the last one is the pseudo-random number generator probing function that we can use. So given a random number generator, we're going to seed it using the hash value of our key, which we know is deterministic, so it's always going to be the same thing. And then we can use that inside our probing function, which is pretty neat, and increment by x each time. And we know x increments by 1, so we're just getting the next number in the random number generator, and then the next one after that. Alright, so here's a general insertion method for open addressing. Suppose we have a table of size n, and here's how the algorithm goes. First, we initialize x to be 1. So x is a constant, a variable that we're going to use for the probing. And we're going to increment x each time we fail to hit a free position. Then we get the key hash just by hashing our key, and that is actually going to be the index where we're going to look in the table first. So while the table index is occupied, meaning it's not equal to null, we're going to say our new index is the key hash, or the original position we hashed to, plus the probing function mod n, so that we always land back inside the table, and then we're going to increment x, so that the next time we run this loop, well, we probe at a different position. And then eventually, we're going to find a free position. We always set up our probing function in such a way that we will always find we will always find a free slot, because we know that the load factor is being kept below a certain amount. Alright, so here's the big issue with open addressing. And it's that most probing sequences that we choose, modulo n, are going to end up producing some sort of cycle, shorter than the table size itself. So imagine your probing sequence just hops between 3 different values in cycles, and your table is of size 10, but you're only ever able to hit 3 slots because it's stuck in a cycle. And then all of those 3 slots are full. Well, you're stuck in an infinite loop. So this is very problematic and something we absolutely need to handle. Alright, so let's have a look at an example. So right here I have a hash table, and using open addressing, and it's got some key value pairs already inserted. And assume that the circle with the bar through it is the null token. Further assume that we're using the probing sequence p of x equals 4x. And suppose we want to insert a new key value pair into the table, and that the key hashes to 8. So that means we want to insert that key value pair at position 8, but oh, it's already occupied because there's key 5, value 5 already there. So what we do? Well, we probe. So we compute p of 1, which is 4x at 1, so we get 8 plus 4 mod 12, well that's 0, so then we go to slot 0 and we see, oh, that is also occupied because key 1 and value 1 is already there. So then we compute p of 2, and then that gives us 16 mod 12, which is 4, and then, oh, that cell is already occupied, and then we keep probing, and as you see right now, we've entered a cycle. So we would keep probing and probing and probing, and we'd always be getting back to the same position. So although we have a probing function, it does not work in this particular situation. The probing function is flawed. So that's quite concerning because not all probing functions are viable. They produce cycles which are shorter than the table size. How do we handle this? And in general, the consensus is that we don't handle this issue. Instead, we try to avoid it altogether by restricting the domain of probing functions that we choose to be those which produce a cycle of exactly length n. And those probing functions do exist. I have a little asterisk here, and it says there are a few exceptions, and this is true. There are some probing functions we can use which don't produce a full cycle but still work. And we're going to have a look at, I think, one of those in the quadratic probing video. Alright, so just to recap, techniques such as linear probing and quadratic probing and double hashing, they're all subject to this issue of the cycles. And what we need to do is we need to find probing functions which are very specific, that produce a cycle of length n to avoid not being able to insert an element and being stuck in an infinite loop. So this is a bit of an issue with the open addressing scheme, but it's something we can handle. Although notice that this isn't something you have to worry about if you're in the separate chaining world, just because we have that auxiliary data structure that just captures all our collisions. Okay, this is going to be a fun one. We're going to be talking about hash tables and the linear probing technique. To get started, let's recap how open addressing works. So in general, if we have a table of size n, here's how we do open addressing, no matter what your probing function is. So we start our variable x at 1. The key hash is just going to be whatever a hash function gives us for our key. And our first index we're going to check is going to be the original hash position. And while the table at the index is not equal to null, meaning that position is already occupied, then we're going to offset the index by where the key hash is plus the probing function mod n. And every time we do this, we increment the variable x so that our probing function pushes us along one extra position. And then once we found a position, then we can insert the key value pair into the table at that position. Alright, so what is linear probing? So linear probing is simply a probing method which probes according to some linear formula. Specifically, the linear function p of x equals a of x plus b, and we have to make sure that a is not equal to 0, otherwise we're just adding a constant which does nothing. I have a small note right here which says that the constant b is obsolete. And if you know why, post in the comments and have a discussion with the others. And as we saw in the last video, there's a slight problem with this currently, and it's that some linear functions are unable to produce a full cycle of order n, and we might end up getting stuck in a cycle. Here's an example of that. If we picked our linear function to be p of x equals 3x, and say our key k hashed to 4, and for some reason our table size was 9, then we would end up with the following cycle occurring, assuming that positions 4, 7, and 1 are already taken by other key value pairs. So the fact that we're only probing at those 3 locations means we're unable to reach all the other buckets, which is really bad, and hence we're again stuck in an infinite loop. We cannot get stuck in this situation ever. So how do we avoid it? So that's the question. Which values of the constant a in p of x equals a of x produce a full cycle modulo n? It turns out that this happens when the constant a and n, the table size, are relatively prime to each other. So two numbers are relatively prime if their greatest common denominator is equal to 1. So that is a and n have a GCD of 1. And when that happens, the probing function will always be able to generate a complete cycle. And we will always be able to find an empty bucket. Awesome. Alright, here's an example with linear probing. So suppose we have an originally empty hash table and we want to insert some key value pairs. And we selected our probing function to be p of x equals 6x and our table size to be n equals 9. And then we also selected a max load factor of alpha equals about 2/3, and the threshold will then be 6. So we resize once we hit 6 elements. Okay, so based on the probing function we chose and the table size, are we likely to run into an infinite loop while inserting, based on what I told you in the last few slides? And the answer is yes. The greatest common denominator of 9 and 6 is equal to 3, which is not 1. So let's go ahead and attempt to insert some elements regardless. We may or may not hit any problems. Okay, so first let's insert, so I guess on the left I have some key value pairs I want to insert, and we're going to insert k1 first. So suppose that the hash value for k of 1 is equal to 2. Then we would say, alright, the hash of k1 plus the probing sequence at 0 mod 9 is equal to 2. So we're going to insert that key value pair at position 2. Alright, next one. So now suppose k of 2 is equal to 2 again. So we're going to try to insert this key value pair at position 2, but oh snap, we have a hash collision. So we're going to increment x and now try to offset at the probing function at 1 instead of probing function at 0. So that is, instead of inserting it now at 2, we're going to insert it at 8. Alright, so that went in because that slot was free. Now let's try inserting key 3. So key 3, suppose that hashes to 3, then we can insert at position 3 and there's no issue. Now notice that we're trying to reinsert k2, which already exists within our hash table. So instead of inserting it, we're actually going to be updating its value because it exists in the hash table. Alright, so from before we know that the hash value for k2 is 2. So then we look at position 2 and k2 is not there and there's a hash collision. So we increment x, offset it by p of 1, and now we're able to find k2, and now we can update the value right there. Let's go to k5. Okay, so suppose k5 has a hash value of 8. So 8 is taken, so we're going to probe, and that leads us to index 5. So we're going to insert the key value pair there. Now let's try to insert k6. Suppose k6 hashes to 5. Then let's probe 1. So now so 5 plus 6 mod 9 gives us 2. Okay, now the hash collision. Let's keep probing. So now 5 plus 12 mod 9 is equal to 8. Alright, another hash collision, so we have to increment x and keep probing. And now we're back to 5. So we've hit a cycle. Alright, so we're trapped in a cycle, but we kind of expected this to happen because we knew that we picked two numbers whose GCD was equal to 3 and not 1. So if we look at all the possible a values we could have selected instead of 6, we see that the ones that give a greatest common denominator of 1 with n, the table size, are 1, 2, 4, 5, 7, and 8, while any multiple of 3 would give us something else. So this comes to the realization that for our choice of p of x, if we choose p of x to be 1 times x, then the greatest common denominator of n and 1 is always going to be 1, no matter what our choice of the table size is, which is why p of x equals 1 times x is a very popular probing function choice. Alright, now suppose we have another hash table and we wish to insert more key value pairs, but this time we're actually going to pick a probing function that works so that we don't ever have any issues. So I'm going to pick the table size to be 12 and our probing function to be 5x. So no cycle should occur. Alright, so let's go with inserting the first guy. So suppose that k1 has a hash value of 10, then at index 10 we have to put k1 v1. Suppose k2 has a hash value of 8, then slot 8 is free, so let's pop those right in there. So now suppose k3 is equal to 10. Oh, hash collision with k1 in there, so we need to keep probing. Alright, so if we use our probing function, which is p of x equals 5x, so that'll give us 3 modulo n when we add it to the hash value. Moving on, insert k4. Now suppose the hash value for k4 is 10, then we have to keep probing. So then we hit k3, which we inserted last time, and then we also hit k2, but we're able to pull out eventually when we hit the third probing value. However, now notice that we've actually reached the threshold of our table. If I go back a few slides, we can see that I picked alpha to be 0.35. So n, which is the table size, times alpha gave us 4. And we just finished inserting the fourth element, so it's time that we resize the table. So how we usually resize the table is via some exponential fashion, such as doubling or tripling or so on. But we need to double in such a way that the GCD of n and a still holds. So after doubling, n is equal to 24, and the GCD property is still good. Alpha is a constant, so it's still 3.5. So our new threshold is just going to be 8, and we don't change the probing function. Alright, so let's allocate a new chunk of memory for this new table. And now we need to place all the old elements in our old table into this new table using the new table size for n. Alright, so if we scan across all these elements, we start at 0, nothing there, move along. So from before, we knew that hash value for k4 was 10, so inside the new table, it's going to go at position 10. Alright, scan along, nothing here. From before, we know that k3 was 10, so it should go in position 10 in this new table, but we have a hash collision, so we have to keep probing. So if we add our probing function at 1, which is 5x, then we get 10 plus 5, which is 15. So we're going to insert it at position 15 in the new table. Keep probing, nothing here, nothing here, nothing here. So eventually we hit k2. So we know from before k2 is equal to 8. So we're going to insert at position 8. Now we know k1 is equal to 10. So we're going to try and insert at position 10. That's taken, so we have to probe. So the next position is also taken, so add 5 again. That gives us 20. So we're going to insert k1, v1 at 20. Alright, So now we throw away the old table and we keep this new table, and this is the new hash table we're working with. And we were at inserting K5. Now suppose K5 is equal to 2, and that spot is free, so we are good. So here's a frequently asked question. Sweet. I know how insertion works. Now how do I remove key value pairs from the hash table using open addressing? And my answer to this is that this topic is going to merit its own video, and we're going to do it after we see all the other open addressing techniques, because it's actually non-trivial. Alright, let's talk about hash tables and how quadratic probing works. Let's dive right in. So let's recall how we insert key value pairs into a table of size n using the open addressing collision resolution schema. So first we initialize a variable called x to be 1, which we're going to increment every time we're unable to find a free slot. Then we compute the key hash, and that's going to be our first index we're going to check. And we're going to loop while we're unable to find a free slot, meaning the table at that index is not equal to null, so it's already occupied. Every time that happens, we're going to offset the key hash using our probing function. Our probing function in our case is going to be a quadratic function. And then we also increment x, and eventually we will find an open slot to insert our key value pair. So what is the idea behind quadratic probing? So quadratic probing is simply probing according to a quadratic formula, or specifically when our probing function looks something like p of x equals ax squared plus bx plus c, and ab and c are all constants, and we don't want a equal to 0, otherwise we degrade to linear probing. But as we saw in the previous videos, not all quadratic functions are viable because they don't produce a cycle of order n, and we might get stuck in an infinite loop. So as it turns out, most randomly selected quadratic probing functions will end up producing a cycle. Here's an example. Suppose we chose our probing function to be p of x equals 2x squared plus 2. The key we wanted to insert hash to 4, and the current table size was 9. Then we would end up with a 2 cycle. So first time around we would probe at position 0, we would get 4, probe at position 1, we get 7. Suppose those two entries were full, and then we would end up in a cycle again. So our probing function is only ever able to hit the buckets 4 and 7, so it makes it impossible to reach all the other buckets 0, 1, 2, 3, 5, 6, and 8. So we're stuck in an infinite loop when 4 and 7 are already occupied. This is really, really bad. So the question then is, how do we pick a probing function which always works? The answer is there are numerous ways, but here are the 3 most popular ways I have found. So the first way is to select the probing function to be p of x equals x squared, and to keep the table size a prime number greater than 3, and make sure our load factor is always kept below 1/2, or less than or equal to 1/2. The other one is to say our probing function equals x squared plus x divided by 2, and make sure the table size is a power of 2. And the last and final one says that p of x should be the alternating sign of x squared, and keep the table size a prime number where n is congruent to 3 mod 4. For example, we could say that our table size was 23 because that's a prime number and it's congruent to 3 mod 4. So any of these will work, but as you see, they're very specific in how they work and what the table size should be, and that's a common theme in quadratic probing. So we're going to focus on the second one, where p of x equals x squared plus x divided by 2, and the table size is a power of 2. Alright, suppose we have an initially empty hash table, and we want to insert some key value pair, and we're using the following quadratic probing function. P of x equals x squared plus x divided by 2, and the table size is a power of 2, so it's 8. And let's select the load factor to be 0.4, therefore the table threshold is going to be 3. So just to emphasize that the table size must absolutely be a power of 2, otherwise this will not work. Okay, so let's insert the first guy. So suppose that k1 hashes to 6, then we're going to insert k1 at position 6. Alright, next k2, suppose k2 is equal to 5, then we're going to insert it at 5, no collision there. Suppose k3 is then equal to 5, then we have a collision, so we need to handle that. So we're going to try probing at offset 1, so that brings us to 6. So we probe again, and that brings us to index 0, which is free, so we're going to insert k3 and v3 key value pairs there. Let's insert k4. Oh, but before we can do that, we've reached the table threshold, so we have to resize the table first. Okay, so let's allocate a new block of memory, and let's double the size of the table to keep it at a power of 2. So our new table size is 16, max load factor doesn't change, however our new threshold is 6, and the probing function doesn't change. So we need to place the entries in the old hash table into the new hash table. So from before, we know that k3 hashed to 5, so we're going to put it at index 5 because we don't have a collision there. Then no element at position 1, 2, 3, or 4. Then we go to position 5 and find k2 right there. So we know from before that k2 also hashed to 5. So we're going to try to put it at position 5, but there's a hash collision, so we probe 1. And then we get 5 plus 1 equals 6. So at position 6, we're going to insert k2. Now let's try and insert k1. And we know from before k1 hashed to 6, but we can't put it there because we have a collision. So we're going to probe along. So we're going to put it in position 7. Alright, and that does it for resizing the table. So let's keep going. We still have a few more elements to insert inside our table. So suppose that k4 equals 35,410. So when we mod that by 16, that gives us position 2. So we're going to say k4, v4 at position 2. So we've already seen k3, and we know its hash value is equal to 5. So since k3 is already in our hash table, we're going to be performing an update. So k3 plus the probing function at 0 gives us 5. So let's update value to be v5 instead of v3, which it was before. So suppose that the key k6 hashed to minus 6,413. So that hashes to 3 mod 16. So that slot is free, so we're just going to insert it. And the last one, k7, suppose it hashes to 2. But we have a collision right there, so let's probe along. So when we probe, our probing function gives us an offset of 1. That's also taken, so probe again. So now we are at position 5, but that's also taken. So keep probing again. So we probe for a 4th time to get an offset of 6. So that gives us 8. And that slot is free. So we're going to insert that there. Alright, let's talk about hash tables and the double hashing, open addressing, collision resolution technique. So just a quick recap for those of you who don't know how we do insertions into hash tables for open addressing. We start with a variable x initialized to 1. We compute the hash value of the key. We set that to be the first index that we're going to check in our hash table to see if it's not null. So the goal is to find an empty slot. So we're going to loop while we are still hitting spots where there are already keys, and every time that happens, we're going to offset our key hash using a probing function. In our case, it's going to be the double hashing probing function. And we're also going to increment our value of x so that we keep probing along further and further. Once we find a free slot, then we can insert our key value pair into the hash table. Okay, so what's the deal with double hashing? So double hashing is just a probing method like any other, but what's special about it is that we probe according to a constant multiple of another hash function. So specifically, our probing function looks something like this. We give it as input the key, which is a constant, and the variable x, and then we compute x times h sub 2 of k, where h2 of k is a secondary hash function. So here's an important note. h2 of k must hash the same type of keys as h1 of k. So if your key is a string, well, h2 of k must hash strings. If h1 of k is, hashes integers, then h2 of k must also hash integers. So here's a note I put at the bottom that notice that double hashing actually reduces to linear probing, except that the constant is unknown until runtime, because we dynamically compute it with h2 of k. So since double hashing reduces to linear probing at runtime, we may be stuck with the same issue we saw with linear probing, which is that we get stuck in an infinite cycle. So if p of x equals 3x, meaning our secondary hash function at runtime calculated a value of 3 for the constant, and say h1 of k was 4, and the table size was 9, then we might end up with the following cycle occurring. So the cycle produces values of 4, 7, and 1, which makes it impossible to reach any of the buckets 0, 2, 3, 5, 6, and 8. So if 4, 7, and 1 are already occupied, that means we're stuck in an infinite loop inside our hash table, and we're not able to insert our key value pair because we're not able to go anywhere else. So this is an issue we have to deal with. So to fix the issue of cycles with double hashing, here's one strategy. We're going to pick our table size to be a prime number, and we're going to compute a value called delta. So delta is just going to be h2 of k mod n, but occasionally delta might be 0. And if that's the case, then we're going to be guaranteed to be stuck in a cycle because we're not going to go anywhere when we probe because we're going to be multiplying by 0. So when this happens, just set delta to be equal to 1. Alright. So here's a justification why this works. So notice that delta is always going to be between 1 inclusive and n non-inclusive. So the greatest common denominator between delta and n is going to be 1, since n is a prime number. So therefore, with these conditions, we know that the probing sequence is guaranteed to have order n. So we're going to be able to hit every single slot in our hash table. So given that there's at least one free slot in the hash table, which there will be because we're keeping our load factor below a certain threshold, then we're going to be able to reach that slot. Okay, so here's the core question. How do we construct our secondary hash function? Suppose the keys we're using have type T. And whenever we use double hashing, and we need to construct h2 of k to hash keys that are also of type t. So it would be really nice if we had a systematic way of generating these new hash functions every time we need one, right? Because we might be dealing with multiple different data types of type t. So luckily for us, in computer science, almost every object we ever create is constructed of the same fundamental building blocks, in particular integers, strings, real numbers, fixed length vectors, and so on. So we can use this to our advantage. Luckily, there are many well-known hash functions for these fundamental data types, and we can combine them when we want to construct our new hash function, h2 of k. Frequently, when we compose hash functions, we select them from a pool of hash functions called universal hash functions, which generally operate on these fundamental data types, which is quite convenient. Alright, let's have a look at an example with double hashing. So suppose we have an originally empty hash table above, and we selected our probing function to be p of x equals x squared plus h sub 2 of k, which is what we need it to be, and our table size to be n equals 7. Notice that that's a prime number, and we set our max load factor to be alpha equals 0.75, so our threshold to resize is 5, so once we hit 5 elements, we need to grow the table size. Alright, so let's insert all of these key value pairs on the left into this hash table. So first key value pair is k1 and v1. Now suppose that the hash value for the first hash function of k1 is 67 and h2 of k1 is 34. And first thing we do is we compute delta. So we compute h2 of k1 modulo 7, which is the table size, and we obtain 6. And then we compute where this key value pair should go, and it should go at position 4. So now k2, suppose h1 of k2 is 2, and h2 of k2 is negative 79. So delta is 5, but we're just going to insert at position 2 because there's no collisions. So h1 of k3 is 2, and h2 of k3 is 10. These are just arbitrary numbers I chose for these hash functions. So then delta would be 3 in this case because 10 mod 7 is 3. So we have a hash collision because we're trying to insert our k3 at index 2, but k2 is already there. So what we need to do is we need to probe. So we're going to compute the position to be our original hash function position, so h1 of k3 at position 2 plus 1 times our delta value mod 7, that gives us 5. So we're going to hop to position 5 right there. Alright, now let's insert k4. So suppose now that h1 of k4 is equal to 2 and h2 of k4 is equal to 7. So let's compute delta. So h2 of k4 modulo 7 is equal to 0 because 7 mod 7 is 0. So when this happens, we know that we need to set delta equal to 1 so that we don't get stuck in an infinite loop. So now h1 of k4 plus 0 times delta mod 7, that gives us 2. So we have a hash collision at the bucket for index 2. So we need to keep probing. So now we probe by multiplying by delta. That gives us index 3. And then we were able to insert. So now we're going to try and insert k3, which is already in our hash table actually, but with a new value. So we're going to be performing an update this time. So suppose h1 of k3 is equal to 2. Actually, we should have known that from before. And h2 of k3 is 10. So we compute delta, so we have a collision, and we find K3, which was already in there, and update its value. Now suppose the first hash function for K6 is 3, and the secondary hash function of K6 is 23, then that gives us a delta value of 2. So when we try to insert it, it goes to position 3, so we need to probe. So we compute 1 times delta mod 7, that gives us 5. There's another collision, so then we compute the offset at 2 times delta mod 7, which gives us 0. And we find a free slot, so we're able to insert our key value pair there. So notice that we've actually inserted 5 elements, so it's time to resize and grow the table because we've reached the maximum threshold. So one strategy when we're trying to resize the table with double hashing, because we need to keep our table size to be a prime number, is to double the table size and then find the next prime number above this value. So in our case, when we double, we get 14, and the next prime number above 14 is 17. So 17 is going to be the new table size. So allocate a new table of size 17 and go through the elements in the old table and insert them into the new table. So from before, h1 of k6 is 3 and h2 of k6 is 23. So we compute delta, and we know we're going to put it at position 3 and there's no hash collision. Next up, nothing in position 1. In position 2 we have k2, so the hash value for k2 is 2 and the secondary hash value for k2 is negative 79 from before. So we compute delta to be 6. So we're going to insert that at position 2 with no collision. Next one, k4. So we know h1 of k4 is 2, and h2 of k4 would be 7. So we compute our delta value, and notice that our delta value now is not 0, which it was before, but 7 because our mod is 17. So delta is 7. So we have a hash collision here, but we need to keep probing. So compute the offset at 1 times delta, which gives us 9 mod 17. Next one, insert k1. Suppose h1 of k1 is 2 and h2 of k1 is 34. Then compute delta, and that gives us 0. So when delta is 0, set it to be 1. So now h1 of k1 plus 0 times delta gives us 2. So there's a collision there, so we need to keep probing. So now compute the offset at 1 times delta. There's still a collision. Keep incrementing the x value. So now 2 times delta, which is 4, and we found a free slot. So insert that key value pair there. And the last one, k3. So from before, h1 of k3 is 2 and h2 of k3 is 10. Delta is then 10. And we have a hash collision. So 1 times delta now gives us 12, and that slot is free. And we reach the end of the new table. So get rid of the old table and replace it with the new table. And let's finish inserting our last key value pair from before, which is k7. Now suppose k of 7 is equal to 15 and h2 of k7 is 3. Then our delta value is 3, and we're able to insert it at position 15. Alright, I know a lot of you have been anticipating the remove video for how we remove elements from a hash table using the open addressing scheme. So let's have a look first at what issues there are when we remove elements if we do it naively. I think this is valuable. So suppose that we have an originally empty hash table and we're using a linear probing function. So p of x is simply going to be equal to x. And we want to perform the following operations. We want to insert 3 keys, K1, K2, and K3, and then remove K2, and then get the value of K3 after. And for the sake of argument, let's assume that we have a hash collision between K1, K2, and K3, all equal to 1. This is a possible scenario. So let's insert them. So K1 hashes to 1. So we're going to insert it at position 1. So let's insert K2. So it has a hash collision with K1, which is already in the table. So we're going to linearly probe. So insert it in the next slot over. Let's insert K3. It also hashes to 1. So let's probe. Okay, another hash collision. So let's keep probing. And finally, we insert it in position 3. Now, we are going to remove K2, and we're going to use the naive removing method, where we're just going to clear the contents of the bucket. To find K2, we hash K2, get 1, but K1 is not equal to K2, so we haven't found the element yet. So then we probe, and then we have found K2. So we're just going to remove it, like so. Alright, now let's query the table and obtain the value for K3. Let's see what happens. So when we hash K3, we get 1. And K1 is not equal to K3, so let's continue the search. And then we hit a null element. So what does this mean? So since the value in the bucket at index 2 is null, we're forced to conclude that K3 does not exist within the hash table, otherwise we would have encountered it before reaching the null position. That's how finding an element works inside a hash table. So this method is clearly flawed. The naive removing method doesn't work because K3 clearly exists within the hash table. We can see it there in index 3. So here's a solution to the removing. When we remove an element, we're going to place a unique marker called a tombstone instead of a null element to indicate that a specific key value pair has been deleted or removed. And when we're doing a search, we're just going to skip over the tombstones. So let's replace the deleted bucket with a tombstone like we should have done and see what happens when we now search for the key K3. Okay, so K3 hashes to 1. So K1 is not equal to K3, so keep probing. Alright, we hit a tombstone, so we know that that element was deleted, so keep probing. Alright, we have found K3, and we can now return its value V3 as our answer for the search. Awesome. Okay, so a quick question about tombstones. I have a lot of tombstones cluttering my hash table. How do I get rid of them? So the thing with tombstones is that we're actually going to count them as filled slots in the hash table. So they're going to increase the load factor, and they'll all be removed when we resize the hash table. But there's also another way to get rid of them, is that when we insert a new key value pair, then we can replace the buckets that have tombstones with a new key value pair. And I want to give you guys an example of how that is done. Alright, suppose this is our hash table of size 8, and we're using the quadratic probing function p of x equals x squared plus x divided by 2, and let's see how tombstones come into play doing this when we want to do a lookup. So suppose we want to insert the key K7 inside the hash table, and the hash value for K7 is 5. So we're trying to find the key K7. So K7 hash to 5, so we check there first. K7 is not equal to K4, so let's keep probing. So we probe quadratically, and we're just going to go to the next slot over, and that's position 6. Now, position 6 is special because it's the first position we encounter which has a tombstone in it. So we were going to want to store this position for later to perform an optimization. Okay, keep probing because we haven't found K7 yet. So when we probe at position 2, we go to position 1. Still no K7 because we have a tombstone, so we have to keep going. Alright, hit another tombstone. So let's keep probing. And aha, we have found our key K7. So we can return the value V7 now. However, we can do an optimization because we don't want to probe an additional 4 times to find K7 because we just hit a bunch of tombstones along the way. So an optimization we can do is to relocate the key value pair K7, V7 to the first position where there was a tombstone. So that next time we do a lookup, it'll be much faster. We call this lazy deletion or lazy relocation. Alright, so we replace the first tombstone there with K7, V7. And now we have 2 copies of that key value pair, so we're going to want to replace the old one with a null token. Okay. Alright, today we're going to be having a look at some source code for a hash table that uses open addressing as a collision resolution scheme. And you can find all of the source code on GitHub at WilliamFiset/data-structures. And then just go to the hash table folder to find a whole bunch of hash table implementations. I have 3 different open addressing implementations here. In particular, we have quadratic probing, linear probing, and double hashing. They're all very similar to each other, so I will only be looking at one right now, but if you're curious, you can go on GitHub and check them out for yourself. The one that's really different, or slightly more different, is the double hashing, but other than that, they are really essentially the same thing. So today I've decided that we're going to have a look at the quadratic probing file, so let's dive into the code. Alright, here we are inside the code for the hash table that uses quadratic probing. So let's dive right in. So I have a class called hashtable quadratic probing, and notice that it takes in 2 generic types, K and V. So this is the key type and this is the value type. So you're going to have to specify these when you instantiate an object, which is a hash table for quadratic probing. So I have a bunch of instance variables that we're going to need. The first is the load factor. So this is going to be like the maximum load factor that we're willing to tolerate. The current capacity of our hash table, the maximum threshold we're willing to tolerate, the modification count, this is for the iterator. Next, I have 2 instance variables that keep track of the total number of buckets being used and the key count, which tracks the number of unique keys that are currently inside the hash table. Now, since we're doing open addressing, we are storing these key value pairs directly inside an array. So instead of having one array with a wrapper class for an entry, I've decided just to allocate 2 different arrays, one for keys and one for values. It makes the code a lot easier and shorter, actually. Okay, this is just an instance variable we're going to be using, or rather setting, when we call the get method. So this is the tombstone I was talking about in the last video. This is the marker we're going to be using for deletions. So every time we delete an entry, we're going to mark it with a tombstone. And we know this tombstone object is unique. Alright, so these are just some default constants. So whenever you want to initialize a hash table without any parameters, you can use these constants. So this is the default load factor. I set it pretty low, but you can change it up as you like. So you can initialize it with a default capacity. And this is the designated constructor. So let's have a look. So the capacity can't be negative or 0. And I check if the user passes in some sort of weird load factor, because we don't want that. So then set the max value for the load factor, then calculate the capacity, and to ensure that the capacity is a power of 2, I need to essentially round up the capacity. So that's going to be with this method next to power. Essentially, it finds the power of 2 that is just above this current number, or it'll also take the default capacity, which itself is a power of 2, so we don't have to worry about that. So either way, it's going to be a power of 2. Then we compute the threshold, which is just load factor times the capacity, and initialize our tables. Alright, so let's get rolling. So this is the quadratic probing function I chose. So p of x, so we give it the variable x, and then we compute x squared plus x divided by 2. So this is a really important method, the normalize index. So given a hash value, it essentially strips the negative sign and mods by the capacity, so it dumps our hash value inside the domain 0 to the capacity, non-inclusive. This is a clear method. This is pretty self-explanatory. Just clear the contents of the hash table and start fresh. Then some helper methods, size, get the key count, and check if our hash table is empty. Then put, add, and insert are essentially all the same method. So let's look at the insert method. This inserts a key value pair inside the hash table or updates a value if the key already exists. Alright, we don't want to allow null keys. If that happens, we throw an exception. If the number of buckets used is greater than or equal to the threshold we're tolerating, we're going to resize the table before doing anything else. Otherwise, we want to calculate the hash value from the key using the built-in hash code method, and you can override this for your particular object. Okay, now I need to explain what I, j, and x are. So I is going to be the current index we're at in the hash table because we're going to be bouncing around. This I value is going to change a lot. Then j is the position of the first tombstone we encounter, if we encounter one. Otherwise, it's -1. And we're going to be using this for an optimization. And then x is just the probe offset, which I've set to 1 initially. Okay, so this is a do-while loop. It's a little long, but it's pretty easy to understand. Alright, so first we check in the key table, have we hit a tombstone? If we have, and j is equal to -1, that means we haven't hit a tombstone yet, so save where we found this tombstone. Okay, so this next check checks if the key table has an entry that's not null, meaning there's a key inside of it. So we have to check if the key already exists within the hash table, so that's what this does. It compares the current key at index I with the key we're trying to insert, this key. And if j is equal to -1, meaning we haven't hit a tombstone, then just update the value. If we've hit a tombstone, then we want to do a swap with the tombstone and up the modification count, and always return like the old value that was there before, just in case you want to use it. Alright, next up, the current cell is null, so we can do an insertion. So j is equal to -1 means that we haven't seen a tombstone so far. So increment the number of used buckets and the key count, and then store our key value pair. Otherwise, we have seen a tombstone, and instead of inserting where at element I, where the null element is, insert it where the deleted token was found. So we're inserting it at j instead of I, so here we're inserting at I, but instead of inserting at j where the tombstone is. And we're going to return null because there was nothing there before. Okay, and if we do a loop, so we get through all these if statements and we haven't returned, that means that we need to keep probing. We had a hash collision and the cell we landed on already had something in it, so we need to probe. So we need to offset where we first originally hashed to plus the probing index, or the probe position, and increment x at the same time. So this will just hop to the next spot. And we do this while we haven't found an empty slot, and we will find an empty slot. All right. So contains key and has key. Just check if a key exists within the hash table. And to do this, I'm being pretty lazy and I'm just calling the get method, and I'm setting an instance variable in there called contains flag, which gets set to true or false whether a key is inside our hash table or not, because the has key and the get method would have essentially the same code, so that's a bad code smell. Alright, so let's look at the get method since it's getting used in the has key method. So same kind of setup. Find the original hash, index is equal to the hash, set j and x to what they were before. So essentially do all the same stuff, or mostly, except set the flag, so that's different. We set the flag to be true when we identify that the key is indeed inside the hash table. And here our else condition is just shorter. We return if we hit a null cell instead of inserting a new element, and set the contains flag to be false. Okay, so pretty easy. And the remove method is actually quite a bit shorter, interestingly. So same setup, check if the key is null, find the hash, set x to be equal to 1. Here we don't really care about tombstones too much, so we don't have a j position. So we're going to start the hash index and quadratically probe until we find a spot. So for every loop, we're going to increment I, or find the new offset position if this loop gets completed. So here's what we do. We ignore tombstones, so we just skip over those. So this happens if the key was not found in the hash table, we can return null. Otherwise, the key we want to remove is in the hash table. And we can do this check because we checked if it's null before, so we're not going to get a null pointer. So decrement the key count, up the modification count, extract the old value, and dump a tombstone here, and just wipe whatever value is in there. So this is where we set those tombstones in the remove method. And then just return the old value for good measure. Alright, and okay, these two methods are pretty self-explanatory. They just return all the keys and return all the values that are contained within our hash table. So the next really interesting method is this resize table method. So this gets called when we're inserting new elements and we need to grow the table size. And remember that in this particular quadratic probing implementation, we always need the capacity to be a power of 2. But since we know that the capacity is already a power of 2, multiplying by 2 will keep it a power of 2. So that's fine. So recompute the new threshold, allocate some new memory for a new table. I called it old table, but it's actually going to be the new table shortly. So here I perform a kind of interesting maneuver here. I swap the current table, that is the smaller table, with this new table, which I call old table, in order to be able to call the insert method down here. We'll get to that. So swap the key tables, swap the value tables, reset the key count and the bucket count. And the reason I called it old key table was because since the swap, well, the the new table is actually the current pointer for what was the old table. That might sound confusing, but I'm using the table we had before to do insertions on, or the pointer to it. Alright, so loop through the old table values, and if we encounter a token or a pointer that's not null and not a tombstone, then we want to insert it. So because we're avoiding reinserting tombstones, we're getting rid of all the tombstones. So even though our table might have been cluttered with tombstones, we're just getting rid of all of them here. Alright, so that's that. The iterator, you can probably have a look at this yourself. It's just looping through all the keys and returning them one at a time. That's a pretty standard two-string method. So that's how you do quadratic probing with open addressing. Today I want to talk about the Fenwick tree, also sometimes called the binary index tree, and you'll see why very soon. This is one of my personal favorites because it's such a powerful data structure and it boasts efficiency, and it's really, really simple to code. So let's dive right in. So things I'm going to be covering in the Fenwick tree video series, just some standard stuff. So go over some motivation, why this data structure exists, analyze its time complexity, and then go into some implementation details. So in this video we'll get to the range query, and in later videos how to do point updates and how to construct the Fenwick tree in linear time. You can also do things like range updates, but I'm not going to be covering that in this series, at least not yet. Okay, so what is the motivation behind the Fenwick tree? So suppose we have an array of integer values and we want to query a range and find the sum of that range. Well, one thing we can do would be to start at the position and scan up to where we want to stop, and then sum all the individual values between that range. That's fine, we can do this. However, it'll soon get pretty slow because we're doing linear queries, which is really bad. However, if we do something like compute all the prefix sums for the array A, then we can do queries in constant time, which is really, really good. So if we set the array P at index 0 to be 0, and then we go in our array A and add that element to the current prefix sum, we get 5, and then 5 plus minus 3 give us 2, and then 6 plus 2 is 8, and so on. So this is an elementary form of dynamic programming right here, calculating all the prefix sums. And then if we want to find the sum from, say, 2 to 7 non-inclusive, then we can get the difference between those two indices in the P array. And that's a constant time thing to compute the sum of the values between 2 and 7 non-inclusive, so that's really great. However, there's a slight flaw in this, which is what happens when we want to update a value in our original array A. Say we want to update index 4 to be 3. Well, now we have to recompute all the prefix sums. So this is really bad because recalculating all those prefix sums can take up to linear time. This is why the Fenwick tree was essentially created. So what is the Fenwick tree? So the Fenwick tree is a data structure that supports range queries on arrays and also point updates. Also range queries, but we won't be covering that in this video. So its construction is linear time, point updates are logarithmic, range sum queries, also logarithmic, range updates, logarithmic, but you can't say add elements to the array. You can't make the array bigger or entirely remove elements. Okay, so let's look at how we can do range queries on this thing. First thing you need to know is that unlike a regular array, a Fenwick tree, each cell is not responsible for itself, but rather for a range of other cells as well. So we're going to say that a cell is responsible for other cells depending on what the value of its least significant bit is in its binary representation. So on the left, I have a one-based array. Fenwick trees are one-based. That's very important. And on the side of that, I also put the binary representation of each of the numbers so you can clearly see what they look like in binary. So if we have, say, the index 12, its binary representation is 1100. So the least significant bit is that leftmost bit. So that is at position 3 in the binary representation. So that index is responsible for, we're going to say, 2 to the power of the position minus 1. So 4 cells below itself. Similarly, 10 has a binary representation of 1010. And the least significant bit is at position 2. So it's responsible for 2 cells below itself. And 11 has the least significant bit at position 1, so it's only responsible for 1 cell itself. So here I've outlined the least significant bits, it's getting really hard to say, for all the odd numbers, which are just responsible for themselves. So that's what the blue bar indicates. The blue bars don't represent value. They represent range of responsibility, and that's really important for you to keep in mind. So now all the cells which have a range of responsibility of 2. Now the cells have a range of responsibility of 4. Notice that all these ranges of responsibilities are powers of 2. 8 is responsible for 8 cells, and I guess 16 for 16 cells. So now how do we do a range query on this now that we're not really working in a standard array, but rather this weird type of range of responsibilities? And the answer is we're going to calculate the prefix sum up to a certain index, and that's what's eventually going to allow us to do range queries. So let's figure out how to do prefix sums just like we did for a regular array, but on this Fenwick tree. So the idea is we're going to start at some index and cascade downwards until we reach 0. You'll soon see what I mean. So for example, let's find the prefix sum up to index 7. So we're calculating the prefix sum from index 1 to 7, inclusive. Usually everything in a Fenwick tree is inclusive. So if we look at where we are at 7, so we can get the value in the array at position 7, and then we want to cascade downwards. So the next guy below us is 6, and then 4. Notice that we're like hopping down. So we start at 7 and then we move down to 6, and then from 6 we go down 2 levels because 6 has a range of responsibility of 2, and then we're at 4, and 4 has a range of responsibility of 4, so that brings us all the way down to 0, and we're always going to be able to go from where we are all the way down to 0. So the prefix sum for 7 is the array at index 7 plus the array index 6 plus the array index 4. Alright, now to find the prefix sum for index 11. So we always start at where we are, so that's 11. And then we're going to cascade down, so the cell directly below us is 10. And 10 has a range of responsibility of 2, so we're going to go down 2. So that's 8, and then 8 brings us all the way down directly to 0. Okay, cool. And one last one, let's find the prefix sum up to index 4. So 4, we start at 4. 4 is a range of responsibility of exactly 4, so that's already, we're back down to 0, so we can stop. Okay, let's pull this all together and try to do an interval sum between I and j. So let's calculate the interval sum between, say, 11 and 15. So the idea is we're going to calculate the prefix sum of 15 and 11. So we're going to calculate the prefix sum of 15, and then we're going to calculate the prefix sum up to 11. But notice that we're not going to calculate up to 11 inclusive, but exclusive, because we want the value at 11. Okay, so if we start at 15, then we cascade down until we hit 0. So 15 has a range of responsibility of 1, subtract 1 from 15, then we get to 14. And 14 has a range of responsibility of 2, because the least significant bit on 14 is 2. Okay, now we go to 12 and then keep cascading down. So the prefix sum for 15 is the array at index 15 plus the array at 14 plus 12 plus 8. Alright, now the prefix sum for up to 11 non-inclusive, so we're going to start at 10. Then we want to cascade down until we hit 0. So 10 has a range of responsibility of 2, so subtract 2 from 10. We get to 8. Now from 8 has a range of responsibility of 8, so cascade down. So 8 minus 8, 0. So now the range sum is the sum of all the indices of 15 minus those of 10. And that's how we would calculate the range sum. So notice that in the worst case, we're querying a cell which has a binary representation which is all ones. And these are the numbers of the form like 2 to the n minus 1. So a power of 2 minus 1. So a power of 2 has one bit set and all zeros, but when you subtract 1, then you get a whole bunch of ones. So if you look at like 15, almost all of its bits are ones, and those are the worst cases. So in the worst case, we might be asked to query, say, 15 and 7, both of which have a lot of ones in them. So we're doing about 2 log base 2 of n operations. But in the average case, this is actually pretty good, and we're going to implement this in such a way that it's just going to be bit manipulation. So this is like super fast. So the range query algorithm is pretty much this. You see it's like literally no code. The range query from I to j, if we have a Fenwick tree of size n. So I'm going to define a function called prefix sum, which does that cascading down operation. So we start at I, and while I is not equal to 0, we're going to sum up the values in our Fenwick tree, and we're going to remove the value of the least significant bit. And we're going to keep doing this until our value is 0, and then we can return the sum. So the range query then is just a difference between those prefix sums. So really neat little algorithm. I want to talk about Fenwick trees and point updates. So let's dive right in. But before we get to that, absolutely make sure you checked out the Fenwick tree range query video that I posted last. Just to get the context of how the Fenwick tree is set up and how we're doing operations on it. Okay. So just to refresh your brain on how we actually did a prefix sum and how we did those range queries. So what we did was we started at a value. at some index, doesn't matter which, and then we continuously remove the least significant bit until we hit 0. So that's the cascading down effect that gave. So let's say we started at 13. Well, 13's least significant bit was 1, so we removed 1. And then we got 12, and then we found out that the least significant bit of 12 was 4, and so we removed 4, and then the least significant bit of 8 was 8, and then we reach 0. And once we reach 0, we know that we're done. So doing a point update is very analogous to this, but instead of removing, we're going to be adding the least significant bit, as you'll see. So for instance, if we want to add a value at index 9, then we have to find out all the cells which are responsible for 9. Because remember, cells are responsible for a range of responsibility. So if we start with 9, we find the least significant bit and add it to 9, and we get 10. So 10, find the least significant bit, has a value of 2. Then we add it to 10. Then find the least significant bit of 12, add it to 12. So that was 4, so now we're at 16. And then we would do the same thing, and then we're out of bounds, so we would know to stop. So if I draw a line outwards from 9, all the cells that I hit are the ones I have to update. So remember, those lines represent a range of responsibility. So the lines that I hit are the ones that I got when I added the least significant bits. Okay, so if we want to add some constant x at position 6 in the Fenwick tree, which cells do I need to modify? So we start with 6, and then we find the least significant bit of 6 and add it to 6, so we get 8. Now find the least significant bit of 8 and add it to 8, so we get 16. So if I draw a line out from 6, then indeed the cells that I do hit are 6, 8, and 16. So the required updates for our Fenwick tree are that we need to add x to position 6, 8, and 16. So the algorithm is really simple. So if we have a Fenwick tree stored in an array of size n, then while so I is the position we originally want to update, so while I is less than n, we're going to add x to the tree at position I and add on the value of the least significant bit of I. And that's it, where the function LSB is the least significant bit of I. And there are built-in functions to do that usually. And we're going to have a look at some source code. Alright, so that was point updates, and now we actually need to construct the Fenwick tree. Let's talk about Fenwick tree construction. We've already seen how to do range queries and point updates in the last 2 videos, but we haven't even seen how to construct the Fenwick tree yet. And the reason I've kept this for last is you can't understand the Fenwick tree construction without having previously understood how point updates work. Alright, so let's dive right in. So we could do the naive construction of a Fenwick tree. So if we're given an array of values, A, and we want to transform this into a Fenwick tree, what we could do is initialize our Fenwick tree to be an array containing all zeros and add the values into the Fenwick tree one at a time using point updates to get a total time complexity of order n log n. However, we can do better. We can actually do this in linear time, so why bother with n log n? Alright, so in the linear construction, we're going to be given an array of values we wish to convert convert into the Fenwick tree, a legitimate Fenwick tree, not just the array of values themselves. And the idea is we're going to propagate the values throughout our Fenwick tree in place. And we're going to do this by updating the immediate cell that is responsible for us. Eventually, as we pass through the entire tree, everyone's going to be updated, and we're going to have a fully functional Fenwick tree at the end of the day. So it kind of relies on this cascading idea. So you propagate something to the parent who's responsible for you, and then that parent propagates its value to its parent, and so on. So it's just kind of like almost delegating the value. So let's see how this works. Oh, one more thing before that. So if the current position is position I, then the immediate cell above us, which is responsible for us, so our parent, let's say that is J. And J is given by I plus the least significant bit of I. Alright? So if we start at 1, well, the least significant bit of 1 is 1, so the parent is at position 2. So notice that there was a 4 at position 2, but we're going to add to 4 the value at I, which is 3. So now position 2 has a value of 7. Now we want to update position 2. So find out which is responsible for position 2. So 2 plus the least significant bit of 2 is 4. So 4 is actually responsible for 2, or is immediately responsible for 2. So go to index 4 and add the 7. Then who's responsible for 3? Well, that's 4. So go to position 4 and add the value at index 3. Now, who's responsible for 4? Well, 8 is responsible for 4. So go to position 8 and add the value of 4. So now in position 8 we have 4. So now we're at 5, and then you see how we keep doing this, just updating our parent, the immediate cell responsible for us. So now 7 is updating 8. But now nobody, well, 8 doesn't have a parent because our Fenwick tree is too small. It only has 12 cells. But the parent that would be responsible for 8 is 16, and 16 is out of bounds, so we just ignore it. It's not relevant. So now we keep going. So I is 9, 9's least significant bit is 1, so J is 10, that's where the parent is. So keep propagating that value. 10's parent is 12, 11's parent also 12, and now we have the same sort of situation we had with 8, where we have an out of bounds situation, so we ignore it. So the values that are there right now are the values of the Fenwick tree. And with these values, we can do range queries and point updates, not with the original array that we had. So let's look at the construction algorithm itself in case you want to implement this. We will have a look at some source code in the next video, but if you're using another language that I'm not using, this could be helpful. So given an array of values we want to turn into a Fenwick tree, let's get the length, which is n, and I recommend you actually clone or make a deep copy of the values just so that you don't accidentally manipulate the values array while you're constructing your Fenwick tree. That could be problematic because we're doing all this stuff in place. So clone the values array and then start I at 1 and go up to n, and then compute j, so the parent, so which is I plus the least significant bit of I. Do an if statement to check if j is less than n. That might actually be less than or equal to n, actually, now I'm thinking about it, because everything is 1 based in a Fenwick tree. Yeah, I'm pretty sure that should be less than or equal to. Alright, let's have a look at some Fenwick tree source code. I'm here in my GitHub repository. You can find it at this link, which I'll put in the description below, at WilliamFiset/data-structures. And the Fenwick tree source code is right here under the Fenwick tree folder. So let's dive right in. I have it here local on my computer in my text editor. Alright, so this source code is provided to you in Java, but it's really easy to translate it to any language you're working in. So I create a Fenwick tree class, which has two constructors. One that will create an empty Fenwick tree for a given size, and then you populate it yourself. And another one which you give it an array of values, like we saw in the last video, and constructs the Fenwick tree in a linear time. So this is probably the constructor you want to use, and not the other one, but I give you the option to use either or. So one thing that you guys should know is that the values array that you pass in, this thing needs to be 1-based. In the last video, I was hesitant on whether or not you had to go less than or equal to the length of the array, and that's going to depend on whether your array is 1-based or 0-based. Usually everything in Fenwick tree is 1-based, in which case it would be less than if you're using this as a length. Alright, but other than that, so this is just the construction algorithm we saw. So just propagate the value to the parent, so that's right here, and ignore it if it's out of bounds. So pretty simple stuff. So this is probably one of the most interesting methods. It's the least significant bit method, and it's going to return the value of the least significant bit for some integer I. So this bit magic right here essentially isolates and returns the least significant bit value. Something that's a bit more readable is this right here, which uses Java's built-in method to find the least significant bit. However, using a raw bit manipulation like this without an additional function call will be faster. Okay, so the prefix sums, this is something we covered in the first video, which allows you to compute the prefix sum from 1 to I, both inclusive. And all this is being done 1-based. So this would do the cascading down that we talked about. So start with the sum equal to 0, and add the values at the indices you hit along the way while you're cascading down. And this line 55, is equivalent to I minus equal the least significant bit of I, which is a lot more readable than this crazy bit manipulation, which essentially just clears that bit. But you want to use as much bit manipulation as you can to keep your Fenwick tree fast, even though it's already really fast. But the more bit manipulation you use, the less operation or machine level operations you're going to do, and so your program is going to be so much faster. Okay, if you want to find the sum between I and j inclusive, then we can call the prefix sum method right here and just essentially get the differences. So that's easy. So adding, so this is if you want to do a point update. At position I and add k to it. So k can be positive or negative, that doesn't really matter. So what you're going to do is, for I, you're going to update everyone who's responsible for you. So all the ranges that are responsible for you. And for each of those, you're going to add the constant k. And then you're going to propagate up to your parent by saying I equals I plus the least significant bit, and you're going to do that until you're still within the tree at some valid index. And this additional method I added for fun is if you want to set the index I to be equal to k. This might sometimes be useful. So just get the value at I, so I to I, and then call the add method. So pretty simple stuff. Now as you see, this is what 80-ish lines, and half of it is comments. So this is a really simple and yet extremely fast data structure. An interesting topic I want to talk about today is the suffix array. This is an incredibly powerful data structure to have in your toolbox when you're doing some string processing. Suffix arrays are a relatively new data structure, appearing around the early 90s due to the heavy memory consumption needs of suffix trees. Let's start with the basics and talk about just what a suffix is. For our purposes, a suffix is a non-empty substring at the end of a string. For example, if we ask ourselves what all the possible suffixes of the string horse are, we are able to come up with 5 unique suffixes. And they are E, SE, RSE, and so on. Now we can answer the question, what is a suffix array? The answer is a suffix array is the array containing all the sorted suffixes of a string. Let's see an example of this. Suppose you want to find the suffix array for the word camel. On the left, I constructed a table with all the suffixes of camel and the indices of where that particular suffix started in the string camel. Then, on the right-hand side, I sorted all the suffixes in lexicographic order in a table. The actual suffix array is the array of sorted indices highlighted in orange. We do not need to actually store the suffixes themselves if we know where the suffix begins in the original string. This is an ingenious idea, and it provides us with a compressed representation of the sorted suffixes without actually needing to physically store the suffixes themselves. All we need is the original string and the array of associated indices. In summary, a suffix array is an array of indices which store the sorted suffixes of a string. Furthermore, for a bit of history on the suffix array, it is a data structure originally designed to be a space-efficient alternative to a suffix tree, which in turn is itself meant to be a compressed version of another data structure called a trie. As a side note, even though the suffix array is very different from the suffix tree, suffix arrays can do just about virtually anything the suffix tree can, with some additional auxiliary information such as a longest common prefix array, which will be the topic of our next video. In this video, we're going to talk about perhaps the most important piece of information associated with the suffix array, and that is the longest common prefix array, also known as the LCP array. The LCP array is an array where each index stores how many characters two sorted suffixes have in common with each other. Let's have a closer look. Perhaps the best way to show what the LCP array is to do an example. In the following example, we'll find what the LCP array is for the string ABABBAB. The first thing we'll want to do is construct the suffix array for our string to find out what all the sorted suffixes are. Notice that the very first entry that we placed in our LCP array, that is the middle column, is 0. This is because this index is undefined, so we'll ignore it for now. To begin constructing our LCP array, let's begin by looking at the first two suffixes and seeing how many characters they have in common with each other. We notice that this is 2, so we place 2 in the first index of our LCP array. Now we move on to the next two suffixes. Notice that they also have an LCP value of 2. And the next two don't have anything in common, so we place a 0. And the next two only have 1 character in common, then 3 characters in common, and lastly, only 1 character in common. So the result is the following LCP array, highlighted in purple. In summary, the LCP array is an array which tracks how many characters two sorted suffixes have in common with each other. Although very simple, you'd be surprised how much information can be derived from such a simple construction. Another thing worth noting is that the very first index in our LCP array was undefined. Since we store the LCP array as an integer array by convention, we usually set this first index to be 0 so that it doesn't interfere with any operations we might want to perform on the LCP array, and this is fine for most purposes. Lastly, we saw what the LCP array was, but not how to construct it very efficiently. There are other algorithms than the one I showed you to construct the LCP array, which run in a much better time complexity. That is, in n log n time and even in linear time. In this video, I want to discuss a neat application of suffix arrays and LCP arrays, and that is finding and counting unique substrings. There are a variety of interesting problems in computer science, especially bioinformatics, that require you to find all the unique substrings of a string. The naive algorithm has a terrible time complexity of n squared, which requires a lot of space. The idea is to generate all the substrings of the string and dump them inside a set. A superior approach is to use the information stored inside the LCP array. This provides not only a quick, but also a space-efficient solution. I'm not saying that this is the canonical way of finding all unique substrings, because there exist other notable algorithms such as Rabin-Karp in combination with Bloom filters. Let's now look at an example of how to find unique substrings. Let's now look at an example of how to find all the unique substrings of the string AZAZA. For every string, there are exactly n times n plus 1 over 2 substrings. The proof of this I will leave as an exercise to the listener, but it's really not that hard to derive. Now notice that all the substrings here, there are a few duplicate ones. I have highlighted the repeated substrings. There are exactly 6 of them and 9 unique ones. Now let's use the information inside the LCP array to figure out which of those substrings really were the duplicate ones. In the table on the right, I generated the LCP array for the string AZAZA. Remember what the LCP array represents. It represents that 2 adjacent suffixes of the original string share a certain amount of characters with each other. So, if the LCP value at a certain index is, say, 5, then there are 5 characters in common between those 2 suffixes. In other words, there are 5 repeated substrings between those 2 suffixes, since they come from the same larger string. So if we inspect the first LCP position at index 1, we see that it has a value of 1. We know that the repeated string is the first character, being A. So we know that A is a repeated substring. The next LCP value is 3, so there are 3 repeated substrings between AZA and AZAZA, namely A, AZ, and AZA. The next interesting LCP value is 2 for the last 2 suffixes, so there are 2 repeated substrings here we can eliminate, Z DSA. We can then come up with an interesting way of counting all unique substrings. We know how many substrings there are, and that is n times n plus 1 over 2. And we also know the number of duplicate strings, that is the sum of all the LCP values. If this doesn't make immediate sense, try out a few examples and play around with it. If we go back to the example we just did with the string AZAZA and we set n equal to 5, which is the length of the string, then we can get the correct answer of 9 by punching n equals 5 and then removing all the repeated substring values summed up in the LCP array. Alright, so if you're looking for a programming challenge concerning counting substrings, like I mentioned here, check out the link to the Caddis Online Judge for some practice. I also included some source code for the suffix array and LCP array available on GitHub at github.com/WilliamFiset/data-structures. There is a really neat problem called the longest common substring problem, or its generalization, the k-common substring problem, which is really what I want to focus on today. First, let's state the problem and then discuss multiple ways of solving it. Suppose we have n strings. How do we find the longest common substring shared between at least k of them, with k being anywhere from 2 to n, the number of strings? As an example, consider the three strings s1, s2, and s3, with the value of k equal to 2. Meaning that we want a minimum of 2 strings from our pool of 3 strings to share the longest common substring between them. In this situation, the longest common substring is BCA, but note that the longest common substring is not required to be unique, because there can be multiple. The traditional approach to solving this problem is to employ a technique called dynamic programming, which can solve the problem in a time complexity equal to the product of the string lengths. Obviously, this method can get unwieldy very quickly, and you should avoid using it whenever possible. A far superior approach, and the way to solve this problem, is to use a suffix array, which can find the solution in linear time proportional to the sum of the string lengths. So, how do we do this? How do we use a suffix array to solve the longest common substring problem? Let's consider the 3 strings we saw earlier, s1, s2, and s3. What we will first want to do is concatenate them all together into a larger string, which I will call t, which is short for text. However, when doing this, we must be careful and place unique sentinel values between our strings. We need to do this for multiple reasons, but the main one being that we must avoid any intermingling of suffixes when we construct the suffix array. Additionally, I would like to note that these sentinel values need to be lexicographically less than any of the characters contained in any of our strings. So in the ASCII table, the pound sign, the dollar sign, and the percent sign are all less than any alphabetic character contained within S1, S2, and S3. So we're good in doing the concatenation. Once we have the string t, we are able to construct the suffix array for t. This procedure can be accomplished in linear time with a linear suffix array construction algorithm. You will notice that on this slide, I am displaying both the LCP array values on the leftmost column and the sorted suffixes of t as they would appear in the suffix array on the right column. I also gave each suffix a certain color to match it with the original string it belongs to. In the slide, you can see that the suffixes starting with sentinel values got sorted to the top because they were lexicographically less than all the characters in the string, and this is to be expected. For our purposes, we want to ignore them because we injected them into the string t ourselves. So back to the central problem. How do we find the longest common substring of case strings, given that we now have the suffix array and the LCP array constructed? The answer is we're going to look for case strings, each of different colors whom share the largest LCP value. Let's do an example with k equals 3. Since k equals 3 and we have 3 strings, this means that we need 1 string of each color. We can achieve a maximum of 2 if we select the following 3 adjacent suffixes. Notice that each of them is a different color, meaning that they came from different original strings, and that the minimum LCP value in the selected window is 2. Note that we must ignore the first entry in the window. This means that the longest common substring solution is the string CA of length 2, which is shared amongst all 3 of S1, S2, and S3. Let's do another example, but this time let's change the value of k to be equal to 2. Since k equals 2, we want to have 2 suffixes of different colors and the maximum longest common prefix value between them. In this case, there is a unique solution, which is the string BCA, with a length of 3 shared between S1 and S2, but not S3. So far, we've covered only some trivial cases. Things get much messier when not all the different colors you need are exactly adjacent with each other. A trick we will use to overcome this will be to use a sliding window technique to capture the correct amount of suffix colors. Here's what we'll do. At each step, we'll adjust the bottom or the top endpoint so that the window contains exactly case suffixes of different colors. Once we have a valid window with the correct amount of colors, we'll want to query the minimum LCP value for that window range. In the picture below, you can see that this value is 2 because the minimum value in the LCP array for that window is 2. Again, ignore the first entry, which is 5. Since the minimum value for that window is 2, all the suffixes in that window do share the prefix AG, which has length of 2, as we would expect. Here are some more details on how we are actually going to perform the query to obtain the minimum LCP value on the current window we are considering. Turns out that this is a pretty popular problem and it can be solved in a variety of ways. Since we're dealing with a sliding window and not just any arbitrary range query, we can use a linear solution from the minimum sliding range query problem to obtain the value we want. Alternatively, I would recommend using a minimum range query data structure, such as a segment tree, to perform logarithmic range queries on the LCP array. This is theoretically a little slower, but it is much easier to implement, in my opinion. So to implement the sliding window, we will also need an additional data structure to keep track of the colors in our window. I recommend using a hash table for this task. On the bottom left, I drew a table to indicate how much of each color we are capturing in the current window. A valid window will require at least k or more columns to have a value greater than 0. In the example that will follow, let's suppose that k equals 3. Meaning all 3 colors will need to be present in our window for a valid query to occur. By a query, I mean querying the LCP array for the minimum value in the current window, and then possibly updating the best longest common substring value found so far. Right now you can see that our window is missing some blue. So our rule when we're missing a certain color is to expand the window down, and when we already meet the criteria, we shrink the window down. So let's expand our window downwards to capture some blue. Now we have enough blue and enough of each color to do a valid query. When we perform the query, we would see that the longest common substring for the window we are in will have length 3, representing the string AAG. Now, since we have enough of each color, we can then reduce the window size. I removed one green suffix, and we still have at least one of each color, so we can again perform a query to find out that we get the same result as last time. Now I shrank the window even more, and now we don't have enough green, so we cannot perform a valid query here. What we need to do is expand the window downwards until we hit a green suffix. Luckily, there was a green suffix right there, and we can perform a query to attempt to update the best longest common substring value found so far. In this window, the longest common substring is only of length 1. So the longest common substring for this window is the string A, which is not as long as the longest common substring we found before, which was AAG of length 3. So we can ignore this one and keep searching. Now we shrink the interval, and we're short one color, and that is red. Let's expand downwards until we reach a red suffix. So we expand and find a blue suffix. This is not what we wanted, so let's keep searching. Then expand and find a green suffix, and keep doing this until a red suffix is reached. This video is getting a little long, so I'm going to break it up here, and in the next video we'll look at a full example of this method being applied. However, in the meantime, if you're looking for a challenge regarding the longest common substring problem, make sure to check out the lifeforms problem on the CAS website. And if you're looking for an implementation of the longest common substring algorithm as I just described, make sure to check out my algorithms repository at github.com/WilliamFiset/algorithms. We're going to finish where we left off in the last video. In this video, I want to do a full example solving the longest common substring problem with a suffix array. For this example, we're going to have 4 strings, S1, S2, S3, and S4. I have also selected the value of k to be equal to 2, meaning that we want a minimum of 2 strings of our pool of 4 to share the longest common substring between them. I have also provided you with a concatenated text we'll be working with, as well as the solution at the bottom of the screen in case you want to pause the video and figure it out for yourself. The first step in finding the longest common substring between a set of our 4 strings is to build the suffix array and the LCP array, which I have displayed on the right side and the left side respectively. While I will be conducting the longest common substring algorithm, notice the variables on the left as they change. The window LCP and the window LCS values will track the longest common prefix and the longest common substring values for the current window, and the LCS length and the LCS set will track the best values so far. So let's get started. Initially, our window starts at the top, and we want the window to contain 2 different colors, so our rule is to expand downwards when we do not meet this criteria. As I expand down, the suffix is green, so we still only have 1 color. I expand down again, and still 1 more green suffix. I expand downwards again, and now we arrive at a blue suffix, and here we are able to perform a range query for our window. However, our query isn't fruitful because the window longest common prefix value is 0. So there's no longest common substring here. When we satisfy the window color criteria like we do now, we decrease the window size. I decrease the window size by 1 and still nothing interesting. I decrease the window size again, and this time look what we found. The current window contains a longest common prefix length of 2, so we obtain the longest common substring, BC, and add it to our solution set. Now we keep shrinking the interval size because we meet the color requirement. Our window size is now too small because K is 2, so we need 2 different color